Let's go to the peak, peak. Let's go catch a time. No globe got you in a bind. Clock stop, found a baseline. Theo angles like these aren't hard to come by. Flat map, we got that design. Refraction caught in a lie. Star clocks record the sky. Hands up, catch that peak line. Occlusion says what's real. Globe math can't seal the deal. Look up, watch the mountain climb. Star drop, measure right on time. Baseline distance, trig so clean. No curve in the sightline seen. Globies say refraction's high, but their numbers don't apply. Flat frame gives the truth in kind. Drop rates lock, stars don't lie. Star clocks record the sky. Hands up, catch that peak line. Occlusion says what's real. Globe math can't seal the deal. Look up, watch the mountain climb. Star drop measured right on time. Baseline distance trig so clean. No curve in the sightline seen. Globies say refraction's high, but their numbers don't apply. Flat frame gives the truth in kind. Drop rates lock, stars don't lie. Star clocks record the sky. Hands up, catch that peak line. Baseline, timing's true. Geometry breaks globe view. Mountains blocking stars like math. Angles trace the occlusion path. Tick-tock, stopwatch, don't delay. Catch the moment night meets day. Globe heads twist, it's just a bend, but the angles won't pretend. Every distance, height, and climb. Flat earth locks the perfect time. Final clocks, no globe to find. Hands up, truth is realigned. Occlusion proves the scheme. Flat earth wins the timing dream. Record the sky, hands up, catch that peak line. Baseline, timing's true. Geometry breaks globe view. Mountains blocking stars like math. Angles trace the occlusion path. Tick-tock, stopwatch, don't delay. Catch the moment night meets day. Let's go to the peak, peak. Let's go.
All right, hello and welcome to Celestial Theodolite update number 16. Tonight we have a couple of things to get through the agenda, and then we will take open questions, have a little Q&A, perhaps a little back and forth, a little soiree, if you will, if some people decide to show up and discuss their choice of presentations on their angles, on how they represent the globe and how versus how we represent the globe. But before we get into that, we're going to have Shane recap on the basics. And then we're going to have Mike touch on his PDF that he wanted to cover, going over the current methodology and tactics used by the Globers to try and refute what's going on right now for obfuscation purposes and not actually addressing anything. So he's going to go over that. Shane, whenever you are ready, sir, everyone please tune into the live stream that Shane is presenting on. And we'll take a look at his introduction video to the Celestial Theodolite to get us back to basics so we can all start fresh and understand the process here, get a fresh look at it from the ground up. Go ahead, Shane, whenever you're ready.
Nice. All right. So there's been a lot of kind of obfuscation, a lot of needless complication, a lot of arguments that aren't arguments, and a lot of contentions that actually aren't refuting any of the things that we're talking about. So I just wanted to take it back to the beginning, really, to the actual observation that we make. And if we notice here, we have the flagship observation. This is Pike's Peak. It's the observation of 39 Aquarii as being included by Pike's Peak. So when we start, this is the only thing being recorded. The only thing being recorded is from this frame. It's just when the star goes behind this mountain. There's no optic angle, as you can see. There's no reticle for you to even measure an angle above the horizon. Nobody knows what angle this is. None of that is going to be used in our analysis. In fact, the only things that we do know are this is Pike's Peak, and we know that it has a known elevation. We know that we are 2,073 meters above sea level, and we know that the distance between us and this peak is 50.7 kilometers. And that's all we know. Those are all the parameters that we need, and that's everything that we're going to be using in our math, in our mutually exclusive predictions. The only other thing that we take from this observation is the time at which this star goes behind this mountain. Our only measurement is this figure right here. These are the only knowns: distance, height above sea level, height of the peak at the time of occlusion. If you're using any other metrics or any other variables or any other parameters that are not listed here, you're not using the correct method. Then it's not the Heffron method. The Heffron method uses only this data, right? So the next part is we're trying to predict based on what we know. Hey, we can construct a triangle to that observation using just the things that we went over, and we can from that create two predictions using simple trig. We do the arctan of the rise over run, which is this over here, the height of the peak minus the height of the observer over the distance between the two, and this just gives us our straight angle, 2 degrees, 31 arc minutes. That's all we're saying. Now, when we're looking at our observation, remember, we don't know what angle it was, but we do know that the time it wasn't visible anymore, the angle of refraction was 0. So if you want to apply refraction to an angle of 0, you're still going to get 0. In any case, that's why we don't use it. What we do, well, what we are comparing is the angle to the star from the peak. And we use the simple trig to do that. Now, to get our comparison for the globe, all we got to do is drop it geometrically, because it would be lower on the globe, by the prescribed amount of Earth drop over that distance. And then we can bring it back up, which we're allowing for celestial refraction from the peak to the star. That's what we're allowing. And that'll give us a mutually exclusive prediction. In this case, that would be 2 degrees, 17 minutes. So then, at its simplest form, all we have are two mutually exclusive predictions. Now again, flat Earth, here's the angle from the peak to the star. And over here is the geometrically dropped angle, is actually much lower, 2 degrees, 4 arc minutes, in which we add our celestial refraction for 2,000 feet at the correct PSI and pressure for the Bennett GG refraction formula, brings it approximately back up to 219. So we're comparing.
Can I ask a question already or no?
Nope, we're comparing 219 to 231. The actual time that the star was occluded was 232. That's what we go into Stellarium and we compare it. So what we're comparing is this angle right here from the peak to the star. This is the magic number. So remember, our mutually exclusive predictions have to compare to that number. And if you notice, flat Earth is much closer than globe Earth. All we're doing is making two mutually exclusive comparisons. So what we get is these two angles. We're saying, hey, in reality, is it occluding at this angle or this angle? Mutually exclusive, flat and globe. And what we do is we compare that over all 43 observations, and the result that we had at Pikes Peak is repeated every single time. What we do then is we create two other triangles using our newly constructed angles, and we can just use the basic tangent function to get the elevation and the distance. So we can construct new triangles. From those observations, we make further comparisons and analyses, and every peak has flat Earth elevation and distance closer to it, never to globe. In these diagrams over here, the true distance is green, the orange is globe, and the blue is flat. The flat in the blue is much closer to the green in each one of these observations because the flat Earth angle is much closer to reality. So what does that mean? Does that mean that the globe is real? Does that mean no? It means that all of the angles that we're observing for the real position of the star correspond to flat Earth angles only. Moreover, it means that the geometric Earth drop that we would have to necessitate if we lived on a sphere of radius 3959 is never present by using this method. And again, most crucially, the only things that we're using are an observation of a peak and a time. Everything that we need to do the method is right here on the screen. If you're adding parameters to this, then you're not using this method, okay? And then when we're referencing the stellarium true position, that's not using the globe. What we're referencing for a true position is as simple as a reference to a first cusp of Aries position, right? That's just an astronomy term. It's known as an epoch. It's just a zero reference, meaning if we're going to reference a point of a circle, everyone needs to count from the same point or we're not going to be able to line up. So this just means the position of the March equinox serves as the 0 point for right ascension and for declination and right ascension, right? The celestial coordinate system. The only point that we're going to compare it with is the 0 point. So if we have the actual first point of Aries over here and it rotates around the world at 15 degrees per hour, that's all we're referencing, is that this is the 0 point, and from this 0 point we count how we're all the way around here in our degrees, in our hours, minutes, and seconds, and that's what gives us the right ascension or the time component for the star. What it looks like in reality is just these are all lines of latitude, and this is a different time. So when we're referencing stellarium, we're only aligning it with this true position. That's the only utilization that we're using. So the nautical almanac reference for where a star appears is not model exclusive, right? It can appear in any model. We know that exactly where the star is because we reference it from the first point of Aries. That's all that we're talking about. So again, we start with our mutually exclusive prediction based on just what we know, and it's very little what we know, which is why it's a great method. We only know that the height of the peak, the distance from the peak, and the time at which it was observed.
Shane, just to let you know that your visuals on YouTube are super zoomed in.
Oh
Let
yeah,
you know.
Oh, are you on the Glowbusters cropping?
Yeah.
Yeah. Didn't quite see all that. You were on a roll. I didn't want to interrupt you.
God
All
damn
right,
it.
you
moving
get it all
forward.
good, Shane. No, restart.
Uh,
no, we can get it off of GeoStream. We're good.
Yeah.
We can just re-up it.
All right, that's all I got though.
Awesome, dude. Great breakdown. So I wanted to add a couple of things to that regarding the first point of Aries. So what I just found recently, I'm going to be doing a presentation on it tomorrow, is actually the first people to use the first point of Aries for navigation apparently was the Chinese after the into the 2nd century. They came out of nowhere with an armillary sphere that uses the first point of Aries, to relate positions of the stars. And they had the difference between their armillary sphere and the European ones was they had an equatorial mount one. And what that does is it tells you the daily sidereal position of the stars versus where the sun's going to be throughout the year, which is what the European one did. So they were distinctly using like zenith positions of the stars, related to the ground for their navigation. And they were geocentric flat earthers using the celestial sphere model. And this is insanely well documented up until the 1600s when the Jesuits came to China and, which is strangely identical to the one that they were already using. It's a really precarious situation. It's a real case of who had it first. But anyway, there might be a little contextual retelling there. So we'll get into that. But the idea that using the first point of Aries or whatever is mutually exclusive is all it does is like it's just that 0 point for your reference for comparison, because with that they just add 15 degrees per hour, and when you do that and you multiply that out, you can, to complete a circle for 360, 15 times 24, you get the you know where that star is going to be at all times. So you just turn time into angles that way. And then they even had methods of timekeeping and all this stuff. So they were, as a geocentric flat Earth framework, right? Because we're all told, you can't do this, et cetera, et cetera. Well, they actually changed their cosmology from their previous one to be a spherical vision of like a limit of vision that's spherical. Solved their issues with the equinox sunsets and all that. So they literally changed their they came out of the 2nd century, changed their entire cosmology, had an armillary sphere, and started navigating with the stars based off of that so that they could have a coherent cosmological model. And then it gets more in depth into that, but that's not really the subject of this here. But I just wanted to point out that just zenith measurements alone of the stars and adding 15 degrees per hour to them doesn't mean the Earth's a ball. Or it could mean that, or it could also mean that you have a limit of vision and the stars went out of your field of vision there. So that was point 1 on that. And then deriving distances and elevations is extremely significant to this process, because when we're doing trigonometry, you can do, most of the time what you're doing inverse functions of your inputs. And what that means is your output isn't going to give you an output that's going to be independent from what you put into it. So in other words, you can hard lock angles into distances, etc., because the inverse function of it has to give whatever that was. So we're going to go over later what the difference is and how we're deriving distances independently, only using one of the known variables. So either using the known distance or the known elevation, we can derive the other thing independently just using the occlusion angle. Whereas when the globe does that with their with what their occlusion angle would be they never get the independence of the distances and the elevations in the same way we do. And another thing to note is because the globe prediction is facilitated by the drop over distance amount, the measurements that we're going to go over here later when I go over the spreadsheet is what we're going to find is that the globe in terms of deriving elevation is always off by what they had to take out. And what the significance of that is that their angle, obviously doesn't match what their occlusion angle, and that's the reason that they're physically off by what they exactly predicted to be on by. So it's a really interesting relationship that we're going to see with that, where in every case they're off by what they predict they should be on by, because if the amount that they predict of drop doesn't physically exist, so they could never overcome that amount when they go back to derive it, or to derive an elevation or a distance. It's so that's another interesting thing to look at and understand. And then we're going to go over some refraction stuff towards the end there. But I think if Shane's good on everything, then we're going to get into Mike's presentation. Mike, if you're there.
Sorry, I'm PDF as soon as I locate it.
No worries. All right, and like I said, we'll get into the Q&A and stuff here in a minute when we're done with the presentation stuff. So just hang tight, be patient. Thank you all for hanging in there.
Okay, and the PDF is shared. And now I have to, okay. Can you see my cursor on the document?
Yes, sir. Mm-hmm.
All right. So I've given this variations of celestial theodolite presentations so many times. This presentation will actually be omitting some things because I want to focus on some lies that are being told, some misdirection. There's a lot of that going on, and I'm not going to cover everything necessarily that I wrote in this document, but you can find this document in the chat. It's called "Where Does the Truth Lie?" And from the point of view of our globe Earth friends, the circumference of the globe is just the circumference of a circle, which is 2 pi r. And for any 2 points on Earth, there's a great circle that allegedly intersects those 2 points. And it's easy to find the radius of that by using the calculators I have links to in the document. So if you go to the actual document, you can actually click on those links and it'll take you right to the website. This is very important to our globe Earth friends because they're often conflating distance with angle. And we'll kind of get into why they're doing that. But basically, they want distance to represent their alleged tilt of the Earth, which I call theta sub d. And that's just the distance times 360 degrees divided by 2 pi r, whatever r is for those 2 points you're trying to find the tilt is the alleged tilt between, which is really distance. And then I give the example of Pikes Peak. Actually, I give an example of an average 6371 kilometer radius of the Earth over a distance of 111.2 kilometers, which is the 69.1 miles per degree that everybody has probably heard talked about endlessly. And for example, at a particular location near my house, and I apologize for little small discrepancies in this between what Shane presented and what this is saying, but at the beginning, I always used Movable Types website to get the distances, and they say Pikes Peak is 50.7 miles from me. Jesse suggested a more accurate NOAA website, and they say it's 50.612 kilometers from Pikes Peak to my house. In any case, that represents the tilt of 0.455 degrees, which is 27 arc minutes. um, and so we're going to focus a little bit more on globe Earth philosophy before we get into how they're using this to lie to us. But we call this science according to the global positioning system. The height above the reference ellipsoid at the summit of Pikes Peak is 4.3 kilometers. So Shane showed 4.299. That 1 meter difference doesn't make any significant impact on the calculations. And also, I say the elevation or location near my house was 2.074 kilometers instead of 2.703. That also makes no significant difference. And then either way, you get a rise of the peak of 2.226 kilometers from me to the peak. So that's the rise. And the distance is the 50.612 kilometers. So if the Earth were flat, the arctangent of that rise over that run would be the plane trigonometry angle of 2.5185 degrees, which is 2 degrees 31 arc minutes. So most of us were indoctrinated as children that the Earth is the globe, and so we're expecting the Earth is going to tilt away from us by that amount. And because of that, our globe Earth friends insist that Pikes Peak should appear to be 0.201 kilometer lower for an observer who's 50.612 kilometers away. And they often call that a d squared over 2r drop. So that's globe Earth terminology. So in other words, Pikes Peak should appear to rise not the 2.226 kilometers that flat Earth would predict, but only 2.025 kilometers above the observer's altitude. And so the arctangent of that rise over run is an angle of 2.2912, which is 2 degrees 17 and a half arc minutes from the observer's location. And that just happens to be the very angle a so-called trained expert measures using a terrestrial theodolite. And I have a little diagram of that there. And so I'm saying, well, that settles it then, doesn't it? But inquiring minds have a few questions, because what our globe Earth friends want to downplay is why don't theodolite manufacturers certify that angle as accurate to infinity and beyond? Because they don't. They say their theodolites are accurate to a few hundred meters. And why would an expert claim a level of accuracy that's far beyond the range of the theodolites? Well, because of that controversy, I decided to perform an experiment of my own. So I went on eBay, found an old David White 8300 level transit, which is a type of theodolite, for $65, and that included shipping. And I decided to measure Pikes Peak. So that particular level transit's only precise to plus or minus 5 arc minutes. But that was more than enough to distinguish between the flat Earth, sorry, the globe Earth prediction of 2 degrees 15 arc minutes, the closest that level transit could measure it, and the 2 degrees 30 arc minutes that globe Earth would predict. And to my surprise, that old theodolite measured the flat Earth angle right out of the box. And I began researching, and there were several problems. Of course, the first problem was that within the precision, that measurement was within the precision of the 8300, but was far beyond the certified range of accuracy for that model of theodolite. Actually, that's far beyond the certified range of accuracy for any theodolite. They just don't certify theodolites to be accurate many kilometers. They generally certify them to be accurate to hundreds of meters. And then secondly, only an expert can use this theodolite correctly. And if you dig into that, you'll find it's very hard to correctly use a theodolite. And then the experts got to compensate for refraction. And the big red flag for me is that refraction is unstable. It comes in many forms, and the experts contradict each other about how to determine its magnitude. And over the past many weeks, Alan's been doing a really good live demonstration of how globe Earth people cannot agree on what the correct value of refraction is. In fact, you find them contradicting each other all the time because they made it so complicated, even they no longer understand the concept. So I had an idea, what if I bypassed the whole refraction problem using a celestial theodolite, find the elevation of the background stars that are occluded by Pike's Peak? Because we've got this constant movement of stars that are being occluded by the peak all night long. And so I should have been able to easily test the null and I'm going to gloss over what a null hypothesis is, but basically if you have a hypothesis that the Earth is a globe, you want to refute the null hypothesis, which is the opposite of what you believe. So if you believe the Earth is a globe, the opposite of your hypothesis, null hypothesis, is that the Earth is flat. In other words, the Earth is not a globe. And if the Earth was flat, that angle should be 2 degrees 31 arc minutes. If the Earth were a globe, that angle should be 2 degrees 17 arc minutes, and that's or at least it shouldn't be 2 degrees 31 arc minutes. And then that would allow you to reject the null hypothesis. So that's the same thing Shane showed a really good diagram of. So I had Gemini AI generate this drawing of a mountain peak, including a star. And this is showing my basic concept. At the time of occlusion, the shadow of the peak falls on the observer because that starry light was hitting the observer's eyes. As soon as the peak interrupts it, the observer is now seeing the shadow of where the star was. And it doesn't matter what that angle may be for the observer. We're taking no measurement, but I show a protractor up on top of the mountain because you can take that measurement indirectly up the occlusion time in Stellarium or your favorite astronomy tool of that star you just saw occluded. And that works because the angle of the starlight and its shadow are congruent angles. So those are known precise angles measuring only at the peak and nowhere else. This has nothing to do with where the observer is. Distance to the observer, the rise of the peak, that all comes into play later when you want to see if that was a globe Earth or a flat Earth angle. But the actual measurement, just as shown in the video that Shane played, is just you see the star disappear behind the peak. You have to identify the peak, you have to identify the star, and you have to have the time. And on that particular video, the video was time stamped, but you could do that with a chronometer, stopwatch, or the best thing for anybody who wants to do this themselves, take a video of it and share it with everyone, and let them know what peak it was. Let them know the location it was observed from, so they can verify it for themselves. And there's a lot of eyes on these videos, and that also helps to make sure that you properly identified the star, you properly identified the peak, etc. For some reason, our globe Earth friends are pretending to misunderstand this simple concept. Some of them call it rubbish. Far too many of them just outright lie or start spewing logical fallacies. And that could be either deliberate or it could be merely insufficient intelligence to comprehend this. But this is not a difficult idea to comprehend. You're citing background stars, and what we want to see is the true location of that star. So analysis using the celestial theodolite is just as simple as finding the occlusion time. And this is a little diagram that kind of illustrates what we're doing. This is an example for Pikes Peak. So for Pikes Peak, it's 50.6 kilometers away. It rises, according to flat earthers, it rises 2,226 meters. According to globe earthers, it rises 2025, appears to rise 2025 meters, and that's because of the 201 meter drop. So that results in a difference in angle. So for flat earthers, the angle would be 2 degrees 31 minutes. For globe earthers, the angle would be 2 degrees 17 minutes. So the object of a null hypothesis is 2 degrees 31 arc minutes. Is the one angle it can't be. That's what you don't want it to be if the Earth is not flat. Well, my very first occlusion, which was 6:43 p.m. Mountain Standard Time on January 27th, and that was just as close as humanly.
Dr. Mike,
Are we losing
breaking
him,
up a bit.
or you stop pushing to talk?
Oh, did you lose my audio?
Yep.
Yeah, cut in and out a couple of times there.
So this may be a network issue of some kind because I haven't touched the talk. What's the last thing you heard that I should back up to?
I think you were just talking about the first occlusion time and how you were able to achieve it.
And actually, I'll make sure the mic is. This is a noise canceling microphone, so it's possible that was causing me some issues. So the first occlusion I ever observed was at 6:43 p.m. Mountain Standard Time on January 27th, and at that time, Pikes Peak occluded the star 39 Aquarii, and according to Stellarium, that was an angle of 2 degrees 31 arc minutes. And that was as close as I could get with my C-Star S50 telescope. And I had that set for 1 second exposures at 1 frame per second in scenery mode. And because this is important, and this is one of the things our Globe Earth friends like to create a lot of confusion about, because the mountain peak itself was physically occluding the star, refraction was not an issue on my side of the peak. It doesn't matter where the peak appeared to be. It doesn't matter where the star appeared to be. Only the peak could have physically occluded the starlight. So that eliminates refraction from the observer side of the peak. Next, I looked up the uncorrected elevation of 39 Aquarii using Stellarium at that time of occlusion. And that made refraction on the other side of the peak also not an issue. Because when you have atmosphere off on Stellarium, it tells you the true position of the star, not where the star appears to be. Well, this was not at all a popular experiment among my Globe Earth friends, so they began making all kinds of arguments. The first one I heard is you can't measure from where the observer isn't. The next argument I heard is refraction is real, so you can't ignore it. Early on, they were saying, "Oh, this is just a coincidence that it occluded the star at a flat Earth angle." And at that time, I had only done that one peak, so we didn't know that they were all occluding at flat Earth angles yet. But those are all fallacious arguments. And what's happening over and over again, and this is why I wrote this particular PDF, is we're getting a lot of half-truths from Globe Earth advocates who are just spouting nonsense hysterically. The best argument they... Say that again?
That's my fault. I was not micing. Yeah, my bad.
Oh, sorry.
No, that was my fault, Dr. Mike. I apologize.
Yeah, no problem.
Sure.
The most coherent argument our Globe Earth friends have is that you need to subtract the alleged 27 arc minute tilt of their Globe Earth from the 2 degree 31 arc minute elevation of the star occluded by Pikes Peak. And when you do that, that explains their 2 degree 4-arc-minute uncorrected elevation of the star at my house, because they want to keep moving the measurement back to my house. And the reason they want to do that, they can then start claiming refraction. And what started this whole experiment is their value of refraction kept changing. Just like you've seen for the past few weeks and everything Alan's going over, they're just constantly throwing out different values of refraction. No matter what that value you use, it's always wrong, but they want to insist that we're never using the right value, and that's why Alan went to the method of back deriving the distance, back deriving the rise, to show you their angles don't work no matter what refraction you allow them to use. But conveniently, they always fix everything with refraction, and that elevates it to the angle that they claim. Well, more than they claim, terrestrial theodolites actually do measure that angle, and that's an optical phenomena. And I don't really go into that in this paper, but they're trying to argue optics, appearances, and the whole purpose of this experiment was to eliminate the constantly changing refraction corrections and to positively identify, is that star occluded at a flat Earth angle or a globe Earth angle? So with all their tilts and refraction corrections, my globe Earth friends have managed to make everyone forget that the occluded star was somehow at the flat Earth angle relative to the peak without any need for any of their tilts, no need for refraction adjustments, without knowing where the observer was. Now they need to know all of those things, and they have to make refraction corrections on top of that to come up to validate their point. This method doesn't need any of that. It eliminates refraction from the picture. It eliminates all the nonsense they keep throwing in to confuse everyone. So not only did my globe Earth friends fail to refute the null hypothesis, they actually validated that the hypothesis that the Earth is flat is true by demonstrating that all of their globe Earth angles are just derived from tilting and refracting the uncorrected flat Earth angle the celestial theodolite finds for the starlight occluded by the peak. So I want everybody to think about that. And I've actually switched to, because in the beginning I was trying to humor them, and Shane showed a good early diagram where it showed that the flat Earth prediction is right between their two extremes, with refraction and without refraction. We're always closer to right on than they are, and yet they consistently claim the opposite because they manipulate refraction until they get the number they want. Well, I've started using a new method, and this graph shows that new method. And I do this because my globe Earth friends, they're lying about what the celestial theodolite is doing. They need tilt and they need refraction to fix their numbers. They need lots of logical fallacies to make their points. When you look at this graph, it kind of eliminates all of that. This is the logarithmic scale on the graph. So that if you know anything about logarithms, you never show 0 on a logarithmic graph, and that's because 0 is undefined. It's infinitely far away. It's like the Zeno's retelling of the Achilles paradox, where the world's fastest runner in a race against the tortoise gets closer and closer and closer, but never beats the tortoise, because no matter how fast he runs, the distance keeps changing and it gets shorter and shorter. Well, so 0 is a perfect globe Earth prediction, and if the globe Earthers were right, all of these gray bars on this graph should be at 0. None of them are anywhere near 0. And the blue bars on this graph are the flat Earth prediction, which is always some number of seconds different from the globe Earth prediction. So where the globe Earth prediction is 0 seconds of deviation, the blue bars show what the flat Earth prediction is, and the gray bars above or below those blue bars are showing what the actual observations were. And you can see, contrary to what our globe Earth friends are saying, everything here is a really, really good match to what flat Earth predicts, and it's not even remotely close to what globe Earth predicts. And this technique begins with just a simple step. Take a time-lapse video of a mountain peak occluding stars. And it's essential to know when the video began and the duration of each frame of the video, and that lets you accurately determine the occlusion times. And then the video also helps document the experiment, and it helps you identify the occluded stars. And when you're having, some people have trouble identifying peaks, and I put a link here to a peak finder website that'll help you identify the peak. And then whatever steps you take after that depends on what you want to know. For this particular graph, what I wanted to know is the actual and predicted occluding times. And to find those, the extra steps I took is I just calculated the predicted flat Earth and globe Earth angles. So one with a drop, one without a drop for each peak. And then I looked up in Stellarium what time each observed star was at those two angles. And then I calculated the difference and plotted that on the graph. So, and anybody who wants to verify all that data in the calculations, out there is a spreadsheet called Coffee Table 2025-08-07. It's an Excel spreadsheet. It's actually saved from Google Sheets, so it's a Google Sheets save of an Excel spreadsheet, and you can refer to that spreadsheet to find any of my data and any details of the calculations. And so this is pretty simple, and I hope interested people will take the time to read this PDF and understand the devious tricks that are being used to try to lie about what's happening here. And that's all I have to say about this.
Nice.
Thank you, Mike. Thank you, Mike. All right, go ahead and close screen share, and I will, inshallah, mine lasts long enough to get through what I got to get through. We'll see what happens here. All right. Couple of things to go over on the basics here regarding occlusions and them being a physical process, because we've been talking about refraction a lot tonight. And one of the things we're often gaslit about is that we're not accounting for refraction. And when they hear things like eliminate refraction, it makes everyone very nervous. Well, another way that you could think about this process is we can actually quantify how much refraction there was at a particular time when a star was occluded by subtracting the true position from the true position of the true position with respect to the star, or I mean with respect to the mountain peak, and also from the true position to the true elevation of the peak relative to the observer. So we can actually see how much lower that star had to get before it was physically occluded versus what the globe predicts for that observer. So a quick recap here on mechanics of occlusions. We're looking at a glass of water here with a knife in it. The knife is going to serve as our physical object. The water is going to be our refractive medium. And the camera is going to be our observer. So the knife is going to be between us and the light source. And what we're going to find here is that the refracted images so the light that's refracted and the refracted knife do not occlude one another. There has to, oops, 1 second.
But you don't have anything to refract it in between the hand and the cup.
1 second. Precisely, because if you can't see, so the purpose of this, right, is to determine whether or not the refracted object can occlude, and if the physical object has to actually intersect, or I'm sorry, if the light source has to actually intersect with the physical object before it occludes for the observer on the other side. And what this video shows as I play it out here is it absolutely does. So the refracted image is not occluding anything when the light source is not intersected with the physical object. When it intersects with the physical object, it becomes occluded. Now we have another example of this here.
But the distance to the
given
star
to
from
us.
the mountain
Please
is
don't
way
interrupt.
farther than...
This isn't for you to interrupt. And also, on top of that, right? On top of that, in addition to that, when the thing isn't visible, it doesn't matter how much refraction is between you and the other object. Let me ask you this, dog. If we're looking at this glass here and there's no we don't see the light anymore, what's the refraction angle on it? There isn't one. So why would you keep proposing that there should be something in between us and this knife to account for when the occlusion process is in the back row? You got your mechanics mixed up. So we're going to continue on now and look at it in another example here. Just hang tight, and maybe your answer to the question you're seeking will make itself available to you. So this is a rig that Goose came up with. Shout out to Goose. So we have this black dowel here. This is going to serve as our observer. Camera here is behind this. This yellow dowel is going to be our physical occlusion. This point source here is going to be our light source. When there's no refraction, what we can show here, this is a side view of it. We can show that as soon as this light source intersects with this yellow dowel here, the observer on the other side can no longer see it. So when you put a stick here to line up where this light source is intersected with the dowel, it's pretty much right on it when there's no medium there. Now, when we increase the refractive medium between the two here, we add a medium. We find that we have to move the light source further down behind this dowel before it actually gets occluded, because it's still visible for the lad over here. And we can quantify that angle here, or by how much further it had to go behind the physical object before it was actually occluded for the observer in between, by putting the stick here and removing the after we remove the medium there, we could put the stick back on the dowel, and we see here that the light source is no longer directly next to the stick. It's a couple inches away. So we're not saying that there is no refraction, right? But we're saying that these angles still produce mutually exclusive outcomes, because the refractive amount isn't 1-to-1. Like for example, if they predict 23 arc minutes of refraction, it can't be the true source of the object can't be 23 arc minutes below it. It's not going to lift it up 1-to-1. That's preposterous. And we'll actually see the quantification of that when we get into that now. So here we're going to start with Pikes Peak, and we're going to look at the relative variables as we continue here. So we have the flat Earth prediction here, which is actually just the rise over run for the distance and the difference in elevation of the mountain peak between us and the peak. So we have what it would truly be at this elevation, and then we have the occlusion timing. So we have the true position of this star with respect to the mountain peak, so we know what angle the star was at the time of occlusion. So in this example, using the true numbers for the peak with our location, we get 2 degrees 31 arc minutes. Using the occlusion timings, we find that the star gets occluded at 2:33 there. So a couple of things we can do with that now. So we can look at we could subtract these two positions from one another and find out exactly how much refraction there was, how much lower that star had to get before it got occluded. So if we kind of look at it like this, we can kind of see some examples here. So in the examples of Pikes Peak, for the observer over here, if you plug in your coordinates to Stellarium and you say that, hey, I'm over here at Mike's house and I'm looking at this star, Stellarium's going to say, hey, the true position of that star is at 2 degrees and 4 arc minutes. And where does that come from? Well, Mike already went over that a little bit, but we'll go over it again to kind of give some names to the faces here. So we have 360 times the distance over 2 pi r squared. That gives us 27 arc minutes. If you subtract 27 arc minutes from the flat Earth prediction there, you get 2 degrees and 4 arc minutes. And that's what this is predicted for the true position. Now they give a 14 arc minute celestial refraction correction to that. So they actually lift this, so this white here is represented by the true position of the star. This yellow one is the refracted position, and the amount of refraction is in between here in the pink. So they predict that it's lifted up at this height. And if you were to get your theodolite out and do an optical measurement of this during the day, you would get about 218, 219, depending on terrestrial refraction between you and the peak. But the purpose here is not to test the optical angle necessarily. It's to derive It's to derive it based off of the occlusion intersections to find out what the true elevation is, the true relative elevation is, based off of our distance. So what we find here, right, when we subtract this out to find out what the actual refraction amount was at the time of occlusion, we find that the star's true position was at 233, and the peak was actually like a little above it because this peak is about 50 meters higher than what they say it is in elevation. So anyway, it kind of looks like this instead of what this looks like. Now this is significant because the 360 times 2 pi r relationship facilitates the 15 degree per hour relationship to move the star where it is. So this first point of Aries true position, the unseen position, the calculated reference that they're using on where it is, tells them that it should be right here. And then they add how much refraction they would have to be to keep it there to maintain usefulness to a ground position with respect to 15 degrees per hour when the star is still visible when it shouldn't be, essentially, because the stars at the horizon don't follow the 15 degree per hour relationship. They linger a little bit. So we're not denying that there's a refraction amount. We're saying that what's given is a computated value that has no bearing in reality. And what we're going to see here is that that's exactly the case, because this refraction amount that they give, what we're going to find is it's almost always half or a little under half by like an arc minute or two of what the actual predicted full drop is from the observer to the star. So they make up the difference in celestial refraction to put it up there in these cases. So now that we have this example here and we kind of know what we're looking at, that the true occlusion happened with respect to the peak and not with respect to the observer, because let's forget about the 201 for a minute here. Let's just focus on what the globe is putting forward with the 217. So let's suppose that this physical peak is up here, and then it's now 14 arc minutes below this before it gets occluded, right? So that's what they're predicting. But in reality, what happened was this star got 2 arc minutes below 233, and it got occluded for the observer down here. Now, optically, right, if you were to get your theodolite out, it might even look like it got occluded at this angle off the horizon, the 217 one. But in reality, the physical occlusion process did not occur until the intersection was with respect to the true position of the mountain peak. And that's extremely significant here because it shows here that this output is just the calculated value after you've told Stellarium where you're at. This was more like you could think of what we're doing here as an external audit of an internally consistent process. Because if you tell Stellarium where you're at, it's going to be like, oh, star's here, it should appear here. But in reality, what happened, the star was occluded up here physically with this process, even though you optically perceived it down here. So that is what we're referencing. So when Shane talks about, then we can construct 2 different triangles to derive distances and elevations based off of this, we can get independent confirmation of the true elevation based off of the occlusion, because we can derive closely the elevation of the peak in our distance in terms of location using angles that are, less than 2 degrees above the horizon. In most cases, it's like a little over half a degree and like a degree and 20 arc seconds, stuff like that. It's extremely small angles here, and typically that isn't done in navigation. So this is like a new thing that hasn't even been really explored yet. Because like I was reading through EA the other day and I saw some of the contentions that some people were putting forward, and they were like, it was basically like astronomers don't even use stars off this low off the horizon, and it's like, yeah, and think about how powerful that is, that we could derive our distance and relative elevation off of that information. Like, that's extremely significant here. So like to ignore that aspect of it is it's just like, imagine being an astronomer and someone's like, hey, I can find my locations with the stars using occlusions half a degree off the horizon. That would be the most interesting thing ever. And like, we have actual astronomers right now that are like, nah, I don't care. Pretty preposterous. So we'll go through a couple more examples here, look at some refraction differences to kind of show you the differences here. So here for Blodgett Peak, we have a distance of 35,000 meters, a relative elevation of 797. Star gets occluded when it intersects at the peak at 1 degree, 11 arc minutes there. The prediction based on the rise over the run for the physical elevation of the mountain. It's 1 degree, 16 arc minutes. So there's a separation of 4 arc minutes of refraction there. And they predicted 17 arc minutes of refraction. So they're a little off there, and they're or a little generous, I guess I should say, and their refractive application. And we've been through how they derive celestial refraction. It's not done through anything like measuring temperature and pressure or anything like that. They take a snapshot of some meteorological data on a particular night. They reference that through several computational inputs where, you know, they basically enter the globe. They start with a observer at the center of the globe with no atmosphere, right? You're just standing on like a little BB at the center of what 3959 would be. And then they extend an atmosphere outward, smooth gradient, all that, all homogeneous, you know, assume all possible static conditions to make it give a uniform gradient to where they can derive exactly how much refraction needs to occur to make that star still relate to its ground position and explain why it has not yet been occluded by the Earth. All right. So hopefully that kind of makes sense on that. And then we'll go through a couple more here. So we got Cheyenne Mountain. 42,000 meters, 810 relative elevation. Star gets occluded at 1 degree above the horizon. The prediction for flat Earth is 1 degree 5, or I'm sorry, the prediction for the relative true elevation of the peak there is 1 degree 5 arc minutes, and there's a 5 arc minute separation for refraction there between the, you know, had to get 5 arc minutes lower before it was physically occluded for the observer 42,000 meters away. And they predicted 18 arc minutes in refraction. And if we look at their drop here, their drop over, how much drop over distance they would predict 23 for the full amount. So they take back, you know, over half of that. And then their drop over distance for that is 144 meters. So if you do 180 times the distance over 2 pi r squared, you get half of the 23 here, so you get 11. You subtract that from their from the total flat Earth prediction there to get the angular amount that the globe would predict. They predict 53 arc minutes, so 142 meters of drop they predict. But then in celestial refraction with their 18 arc minutes of lift there, that actually gives them, where's my lift? Celestial lift. That gives them 230 meters of lift if you were to reverse how you instead of making it an angle, you make it the numerical value. So you just get the distance, or like what it would be what it would be as if it were a physical elevation. So they predict 230 in lift when they predict 140 in drop. So they, like, you know, double the compensation there. And then what was the other part? Can't remember the other part. We'll continue on here. Blue Mountain, same scenario here. 49,000 meters, 829 relative mountain elevation. Star gets occluded at 1 degree above the horizon with respect to the mountain peak. The stats for the peak prediction based off of rise over run are 1 degree, 4 arc minutes. They predicted 13 arc minutes and drop relative to the peak from the observer. And then they made that back up in 18 arc minutes and refraction. So with a drop over distance of 194 feet or meters and drop over distance, they have a lift of 273 meters. So that's very cool. And then the actual amount of separation was only, you know, for like the true refraction value would be 3 arc minutes of refraction there. And we'll do, so the biggest cases that we've seen where Jesse's measurements on Blinn Mountain there, there was 12 arc minutes of refraction between the true position and the peak there. So that's the highest amount that we've seen, and that was at 1 degree. I'm sorry, that was like basically at sea level, like 5 feet above sea level, and the angle there was, what was it? 1 degree 43 or 1 degree 34 arc minutes. And then we have Goose, who did one at the same elevation, so super low elevation, but the angle was a little higher, 43 there was only 4 arc minutes of refraction. So definitely that tight angle with the below sea level definitely gives a significant increase in refraction. But if we look at the prediction versus how much was physically there at the occlusion time, there's 12 predicted here for Blinn Mountain, and then they predict a hard 20. So for For 38 meters in drop over distance for that, they predict 100. There was one to cover quick.
Roboting hard, dude. Maybe you're back? No? Nope. Nope, still very much robotic.
I have a question. If it's question time.
I don't think it's question time. I think it's robot. Yep, robot time.
I think we could squeeze in a question time, maybe.
Well, my question is, so if Earth is a globe, why is that star disappearing like it's flat?
That's a very good question. Well, I mean, we're just trying to compare geometrically different, the difference between globe and flat. Does the surface curve at that rate? And we're using, stars occluded by mountain peaks to do it. At its heart, that's all that's going on.
Testing 1, 2.
There you go.
Whew, sorry about that. Almost made it through the whole thing. I'm just about done here.
Good.
You were on the part about the angles.
Yep. Pikes Peak, Aquarium. All right, there we go. Sorry, just a second. I got to put everything in Pikes Peak because that's my frame of reference for determining everything data-wise. Okay, so what we were looking at here is also we're deriving distances and elevations based off of the occlusion angles. And the point to do this is to do it so that it's independent of one of the other variables, because if you use two of the other variables to get the other, then when you do the inverse functions, you're not going to get anything unique out of that process. So the idea here is to independently find our distance and relative mountain elevation based off of only knowing one of the other two variables. So like Mike was saying, if we only know the star name, the time it was occluded, and the time that the star was occluded, and the mountain peak, we can look up everything we need to know to derive our distance, because we just do the arctan of that and we get the distance. Now, on the same respect, we can take our distance and the angle and derive what the elevation would be. So we can have two different ways to derive the relevant information there. So when we do this, we end up being pretty close here. We're off by 30 meters for elevation, and we're off by 666 for distance there. And then when we look at what the globe is, they end up being off by, when we do theirs based off of their physical occlusion angle, what they would predict. So how they predict that their occlusion process should be down here physically, we take the comparison there, and they end up being off by 201 meters. Where's that? Where's that familiar? Oh, that's their amount of horizontal drop over distance to the mountain peak. And this relationship holds for every single peak, because their initial starting prediction was that that physical elevation of that peak is actually lower because they think that we live on a ball. So relative to where they're at, that peak is going to be, minus, in this case, for Cheyenne Mountain, 142 feet lower. And then when they go to derive elevations, they end up being 143 off. And that's just a rounding thing. It's the amount's identical. So that's another instance there of them not being able to derive the anything correctly. Now, in some cases, when the angles get really small and the elevations are really low, they end up being within like an indistinguishable range between the two. So, but other than that, they're always off by what they predict. Even within the ones where where it gets indistinguishable, they still end up being off by 38 meters. They predict 38 and drop. Same scenario over and over again. All right, and then one final thing on calculation. So last week we went over what was that picture at? I don't even, hang on a second. Uno momento. Where was that picture at? There you are.
Can I say something?
Sure.
Okay, so I live in Denver. I have been in the tower at Elitch's Gardens, and I have looked south. You cannot see Cheyenne Mountain from there. Why is that?
Nice. All right.
The Earth is curved.
Fantastic. All right. So we were given this last week, this 42 arc minute angle, which is what they would predict for the optical angle there. And then when you derive the distance off of that, they're like, look, it comes out to be what it was. Alan's lying. There's more globe underneath the globe that wasn't accounted for. Nope. That's not the purpose here. The reason that it comes out identical is because it's hard locked into it. So if we change the distance here, we just hard change this distance. Oops, change it to the same amount. That'd be funny as hell. Change it to 80,000. The distance now becomes 80,000. So if I go up here and change my distance to what I'm calculating my stuff off of, if I change the distance here, my distance prediction doesn't change because it's based off of the elevation and the occlusion angle. It's not tied to the original distance itself. Wait, what did I just? Oh, I changed it only by 500. Sorry, let me change it by a more significant number. So it doesn't change. How much I'm off by would change because it's comparing the derived elevation over the true. So I mean distance. Sorry. So the distance changes, but my actual derived distance doesn't change because it's not tied to it. So if you can't do it without it being circular, it serves no purpose and it's deceptive. Like the whole purpose of this is to do it independently, to actually test the globe, to put the globe to test, not to use inverse functions of your input to calculate to have your output resemble your input. That just means you can shuffle numbers together and divide. That doesn't tell us anything unique about where we live using this process. So I think that's all I got there on the updates for the refraction stuff. So a work in progress thing that I'm working on now that I have the correct refraction amount there, we'll be able to do some ratio comparisons for basically a refraction compensation index, so we can get some ratios to figure out, like, are they compensating by 100%, 80%, and how much of the refraction was actually wasted due to overcompensation, et cetera. So we can get some nice analytics off of that. But other than that, that is what we are putting forward. And to answer your question about why you were muted, is we are not doing optical angles. If you think something isn't visible because you're far enough away from it that globe drop occurred, our argument is that it's optical, and we're settling the matter using star occlusion. So you came in super hot, way off topic, and this just just got to take a minute to settle down and get adjusted to the conversation here. All right, I am now done presenting. So if anyone has any questions, we can take it up to an open Q&A now.
Well, I do. I don't mind letting somebody else go if they want.
Yeah, anybody else probably would be good.
What happened?
John wanted to know if he could come up here and repeat the same argument that he's been making about the optic angle from the peak being 219 and observing with an agreement when you change the whole process and change the observer location. He's going to say that 7 or 8 times, 6 or 7 different ways if you want to let him.
I wonder if I get to
No,
just
of
say
course not.
something for
No,
1 minute.
we don't care about the optical angle. That's not what's in contention. We're
So
specifically
you don't,
using a
you're
physical
not gonna let
occlusion
me talk.
process. And I think it's really interesting that you keep wanting to do this thing where we're deriving distances, elevation, showing significance over it, and you're like, but my optical angle. Like, the point of this isn't to stifle conversation, it's to help people grow and understand and get clarity on it. We're not disputing the optical angle. We're trying to find out if the optical angle is true or not. We can't reference the optical angle itself to find out whether or not it's true. So we're using an external process to test it. If you don't like that or disagree with it, your contention's noted, but we don't care.
All right, but was John doing an optical thing or?
Always.
John, were you going to go optical, John? Is that what you were going to go with? John?
Oh, I thought I was still server muted. Well, I was just going to simply do what Mike was talking about. Mike was, can I have 1 minute? 1 minute. That's all I need. Do I get 1 minute?
5 seconds left.
Okay, so I just as I've posted a couple times, just put a picture in the chat there. By definition, I mean, the picture helps, I think, for people to really understand. When you see a stellar occlusion, it is because you see the star at the same place as you see the peak. That's just the definition of an occlusion. And Alan has even told me that he couldn't agree more with that. So I don't know if he's changed his mind about that, but that's just the definition of an occlusion. And as Mike said, the geometric elevation angle of Pike's Peak on a flat Earth is 2 degrees 31 arc minutes. On a that might get lifted by 1 or 2 arc minutes, negligible if you include refraction. On a globe Earth, the elevation, as Mike also said, is 2 degrees 17 arc minutes, and that gets lifted negligibly to like 2 degrees 19 arc minutes. At the time that Dr. Mike saw the occlusion of 39 Aquarii, Pike's Peak, Stellarium reports that it was visually 2 degrees 19 arc minutes above the horizon, and that agrees with the elevation angle determined with a real theodolite, and there's nothing more that anyone needs to know.
All right, so that is
I'm
exactly
done.
what you're doing. It's
Is it?
exactly.
All right.
That's exactly what I said.
All right.
Yep.
So
exactly what they said you were going to do. So, John, can you steel man why that's not what this method is?
No, Joe, he actually can't. I don't.
No,
I'm about to cover it right now. I don't care, John. Explicitly, why not? So this is why we go over the occlusions being a physical process and why I just went over all those refraction statistics. Because the occlusion being a physical process, they have a 14 arc minute separation between what they're predicting here for their physical relative elevation of 217. He called it 218 because of terrestrial refraction. But as we went over earlier, terrestrial or refracted objects don't occlude things. So that's not being considered here. The actual intersection, right, would have occurred at this range right here. With their 14 arc minutes of cell refraction, they predict it's already below this. So when he's saying, oh, look, we're just looking over here, and that's exactly what Stellarium predicts after we already told it where we're at. Cool. Don't give a shit. This is BS. This amount right here doesn't work. Want to know why? Because in reality, when the star intersected here at 231, there was only 2 arc minutes of separation between the true position and the peak of that to cause the occlusion that he's referencing for the optical down here. That's explicitly why we don't care about the optics. So for him to do that repeatedly for the umpteenth time is explicitly why he's not allowed to participate in this. Complete time waste detracted from everything.
But it does show that the globe actually has no answer for the actual proposition, for the actual angle, for the true occlusion time. It's always flat Earth. So as soon as they realize realize this. They just immediately all forgot what it was about and pretended that it was about an angle that was never observed. Remember when we started, the only parameters that we have to do any of this for is the elevation of the peak, the distance from the peak, the height of the observer above sea level, and the time of the occlusion. There literally is no observed angle in that equation, in the data set, in the parameters. It's not used in our predictions, our comparisons, and our math. So for you to try to insert that and then try to compare that to the method is retarded.
Well, are you saying that the mountain is not refracted? The peak of the mountain that is going to occlude this star, is that not refracted? You're saying that can't?
Well, when you can't
have a mountain that's...
Sorry, Zanny.
When you can't see it, it's been fully obscured by the mountain peak, whatever the refraction amount is, whatever you want to consider it, etc. At some point there, the physical intersection point was crossed, and that's all we care about when it's no longer visible.
But the mountain could be refracted, and the position of that peak and the occlusion point would be
but if it's not visible, yeah, and that's fine. So that we actually quantified that.
Are you agreeing with me? Are you agreeing with me?
Yes, Zanuck. Yes, Zanuck, we fully quantified that at the beginning of the presentation with the Dow setup. So if you take a look here at the screen share, I have a light source with no refractive medium between us and this Dow here. This is going to serve as our occlusion object. This black Dow here is going to be our observer. We have a camera over here that's watching from the perspective of the Dow. It's looking at this occlusion object, looking at the light source. When the light source intersects with this object, it's no longer visible for the observer over here. We then put a stick across the two to line up, and we see that the light source here is just barely intersected with that Dow before it stopped being visible for the observer down here. Now we add a medium over here in between the observer and the occluding Dow, and we find that the light source.
By the way, great presentation. I'm understanding it like a ton more.
That's great. In the what we find here is that the light source has to physically get further behind the Dow before it's occluded for the lad over here. So there is refraction. We don't dispute that, but it still results in an occlusion angle that has to occur when it's no longer visible. And when we do the when we put the stick back here to check the alignment, we see here that these angles are not the same. It was pretty much right next to it, and then now it's like a couple centimeters off. I forget the exact amount, or it's like an inch off or something like that. I forget the exact amount, but it's off now. You can clearly see that. So when we get into the data here for the occlusions, we have the celestial refraction amount at the time and the relative angles for all of that, and we have the true elevation of the peak using rise over run based off of the distance and the elevation of the peak. And we note that the intersection. 1 second, and we 1 second. I'll tell you. Just give me 1 second. When we subtract the difference between the two, we find that the star only had to get 2 arc minutes below the peak before it was physically occluded. Now, if the Earth were a globe, right, then what would happen is the star would be 2 arc minutes below this 217 angle, and it would get occluded right around here.
We'll start now.
Up in this 231 range. It would be what the globe actually predicts. Now, to get the distance, you said, we take our latitude and longitude coordinates, and we take the coordinates of the peak, and we use a website called Movable Types to get the difference there to calculate the distance between the two.
So you have an arc, according to the globe model, that'll be an arc distance. It won't be a line of sight distance.
There's several different ways you can calculate. I have a line of sight one. I have an arc length. I have a great circle length. There's different ways you can calculate it. No one's disputing how the distance is calculated between the 2 points, though.
I would be. I mean, that could be, that peak could be have all sorts of anomalies of shapes, and you can have a peak of Pike's Peak 500 feet farther back, at 500 feet higher, and a mile or two farther in on the mountain to be blocking something.
You certainly could, but we didn't, and that wasn't present, so that didn't occur.
So what part do we know? See, if you had something like an observatory where you saw a star occluded by the actual observatory, you'd know exactly where it is. But see, even then, if you're looking at some other resource to find the distance to it, you're going over land. The land is assuming to be curved. All you really can do is look at its angular size and figure out its distance to that object that you know the size of.
Listen, big dog. Let me save you some time here, Zanuck. This is a link to my spreadsheet. You can go here, make a copy of it, and you can put in any distance derivation you want between the observer location and the peak. and fill in the blanks, and you let me know if there's anything off or how much it was off by or anything like that. I'm not going to listen to a bunch of hypotheticals and what it could be and all this stuff when we have the exact figures here per thing. Like, that's preposterous. I'm not interested. You can quantify it, or you can, send me an email. Otherwise, your contention is noted.
Well, that's just one of the contentions, obviously. I mean, in other words, we look at more simple observations of just mountains. I mean, we're looking at the mountaintop. It doesn't really matter whether it occludes a star or not. And the occlusion angles are out of stellarium are incorporating round Earth also, but it doesn't really matter. We want to see.
No, that's not happening at all. Hold on,
Well,
because
how about this? Can you tell
all
me,
right, dude.
can you tell me the angle for which that object, that Pikes Peak object, should be for a flat versus a round Earth for the given distance?
For a flat Earth, 2 degrees 13 degrees 17 arc.
You were roboting really bad. All I hear was 2 something. One more time. It's still doing it. Hang on a second. It's really bad. You've probably gone away.
He said 2 degrees, 33 arc minutes, and 2 degrees and 17 arc minutes.
17 arc minutes and 33 arc minutes, you said?
Yes.
So off by about 15 arc minutes. So a quarter of a degree.
Testing 1 2. Can you hear me okay?
Yeah, it sounds good now.
Yes,
In your
they're off
spreadsheet,
they're off by 13 arc minutes or 200 meters.
So what about when you look at other mountains that are in the distance? That's kind of the gold standard for really seeing this effective curvature. Are they aligned for if they're twice as high one another, twice as far away? That kind of equations. Do you have another mountain in the field of view that can...
Yeah, you're actually completely lost here. We're doing occlusions and deriving distances and elevations based off of that. We're not optically comparing things or anything like that.
But the contention is on as you're saying, the globe side. They're saying that they are seeing these things at these positions that resemble the angles of a round Earth. They're saying that they've been loomed up, right?
Yeah. So if the curvature is physical, though, then as we went over earlier with the occlusion process being physical, then the angle has to correspond to an intersection that would be at a lower elevation because the mountain is physically lower relative to us. So we don't care how it optically appears. In fact, that's we're testing that. We're seeing if that's physically corresponding to the elevation that's being asserted. And what we found, it's not. When we
You're looking at something that's
oh my God, buddy, we're not even looking at anything. Like, the fact that you're trying to jump in and tell me what we're looking at is
Let me
insane,
finish the sentence,
because
and
we're
maybe you'll understand
comparing
what
an
I'm saying.
occlusion timing for a star that we don't even see. So, like, you don't
Okay.
really even know what we're looking at, and it's annoying that you're like trying to jump in and play globe defense lawyer, and you don't even really know the process at all. Like,
No,
I
I
don't
do know
have
the
the
process, and
patience
I'm
to
just trying
continue
to...
going through with it
I'm
with you.
just trying to...
Let's
I just
start
want to see if
with the basics first,
Wow.
instead of you trying to refute it off the bat with knowing absolutely nothing about it, because
I'm
that's
not
just going to
refuting. I'm just
irritate me to
asking
infinity.
questions. I'm just asking questions. You're letting me even answer the question. You don't even know what my question is, and you're talking over me. My question was, do you understand, or do you have incorporated into your calculations and your kind of logic here that the mountain, because your example in the lab example on the ground had some fixed refractive element in its path, which is a very short distance over the entire distance of that observation. Similarly, from your observer to Pikes Peak to the star, it's a very vast distance. And if the mountain is refracted something, that doesn't have anything to do with how much the star will be refracted, because it's so much farther away. Going through much more atmosphere over a vast distance until there isn't any more atmosphere, and it's out in space. So that's one of the reasons why the sun will drop a half a degree, but the oil rigs 8-10 miles an hour will only be 0.02 degrees. And we're talking about a huge, dramatic difference. A half a degree, 30 arc minutes compared to 0.02 degrees. I just wonder if you considered that, or if that was something in your thought logic process.
Have you considered that when the star isn't visible, it's not being refracted anymore because it's been occluded?
Yeah, when you don't see it, and how much when you're adding to an angle of 0, how much is that refraction going to affect the end result? And if my angle is 0 and I add a refraction to it, what's my ending angle?
So you're saying when the sun is
Is it 0? Is it still 0?
No, it's not 0.
Okay, so you add so okay.
It had a greater angle of refraction than the mountain in front of you, because the differential version of Snell's law, which does a continually change of angle.
Is there a differential version that lets us see it when it's been fully occluded?
Hold on, all the way to the mountain.
Because like you keep talking past it, like it not being seen is
I'm really curious
insignificant.
as to your answer.
If it's not seen, then there's nothing to calculate off of, dog. We only care when it's not seen. What did the positions happen to be when its star wasn't seen anymore? Was the true position at this over here? Was it down here, or was it up here? That's all we care about. When this star, when we can't see it, when it goes bye-bye, when the star goes night-night behind the mountain, what angle did it happen to be at? We hop into Stellarium, we enter the peak coordinates, and we go, oh, star was right here. Cool. It wasn't right here. Interesting. Guess that means it's not a globe. We don't care about what's going on between here and here. We don't care about what's going on between here and here, because what's going on between here and here already happened, and we can no longer see the star now. And we look at our stopwatch and we go, oh, because time equals angles to stars, we can now reference where the star is at this time. Let's take a Gandy here and see which angle these happen to be at. That's all we care about. You're taking it to a place that's completely unnecessary.
What time are you using the equal star?
GPS time.
15 degrees? I don't know, 15 degree per hour?
Just regular time. Whatever the time is. Your local
do they move?
time.
Do they move in proportion?
Your local time.
I guess what I'm asking is, are you looking due west or due east?
It actually doesn't matter. You could do east or west. West would be occlusions. East would be emergences. No, I said east or west doesn't matter. You could do occlusions or emergences.
No, the question is east or west. You can't. If you go north, it's not going to work as well, right?
West in this scenario. I said you could do east or west.
I know that. I was just asking if it was exactly west.
Oh, sorry,
okay.
West.
Yeah, I think I take a look. I'll look at your spreadsheet. How do I get a hold of that thing?
Nice. Sent the link right here. Here's the link.
Hey, does anyone have an actual question about the true position and the comparison between the two angles that the whole sheet is based on, that the whole method is based on? Does anyone have a question on that? I mean, we can entertain optics arguments ad nauseum afterwards if y'all just want to admit that the first method as presented is flat Earth all the time. But if we're just going to pretend that it's related to optics.
It's not related to optics, it's actually related to everything, because you have a star that's moving downward at some rate. And whatever that rate is, you've done the stellarium, and if you've measured it yourself, and then it starts to be occluded, then it becomes occluded. Right at that point, you're like, okay, boom, that star is, I can't see it. It's right at that peak, and if it is refracted at a half a degree versus the mountain, which is refracted only at 0.02 degrees or maybe less, what does that mean for your conclusions?
Refracted mountain doesn't mean anything.
What's not refracted in your field of view is based on the distance and the height and the elevation of it. Compared with the star, they're not going to be the same. So that obviously the occlusion will be incorrect for using that as an angle to where it is in the field of view, because it would be refracted more than the mountain itself.
You'd think so, but that's not what the occlusion time tells us. So wrong every time. You would think so.
Experiment that was on the floor that had 1 point of a light bending due to the differential medium. Only one.
Nah.
You had two angles, not infinite angles over far greater distances. I mean, many orders.
We're basing it off of actual occlusions, and then now we're quantifying it based off of subtracting the difference there. So like the same thing that we did with the Dow, we're doing the same thing with mountain peaks now, and we're finding that the actual refraction amount isn't even close to what's predicted.
Well, I'll tell you,
because the occlusion can't be 1-to-1. Oh, did you just think of something in the middle of me explaining my thoughts? That's fucking tight,
dude. Fucking Sandy.
Dude, anyway. All right.
But like, yeah, I'm genuinely curious.
Questions?
Any real questions about the process as we outlaid it, using the limited parameters as provided? Anything on that? Like, just like, the basis of the method.
Yeah, has there been any valid refutation yet?
None. Guys, we can derive our distance and location. Some dude just linked a fucking standard deviation thing and was like, it doesn't even work with its own. Like, what are y'all talking about? Hello, guys. Distance and elevation, we can derive it based off of when the star isn't there anymore or when it just suddenly appears. And when we subtract the differences off of what they predict for when that should occur, it's not even close to the refracted values. Is anyone going to use a globe elevation angle to derive their distance and elevation? Or is it going to be a bunch of not that?
Alan, earlier you made a comment about astronomers ignoring this or not looking at it. Can you explain that a bit? Like, what do you mean by that?
Yeah, I don't want to put anyone on blast or whatever, but there was like, a mainstream astronomer that's part of the community here that recently put a video out and was like basically an 8-minute video that said, I don't know anything about the process, but other people have said they debunked it and I heard they don't include refraction, so I'm not interested in it. And when I tried to tell said astronomer about how we're not doing any of what he said and he's been misinformed and we can derive our distances and elevations based off of this, his response was, I don't care. You're not incorporating refraction correctly, even though I can't incorporate it any harder. Like, it makes so not, this is like outside of the flat Earth, globe Earth paradigm, right? Finding your distance 1 degree, using star occlusion sub 1 degree off the horizon is a pretty impressive feat. That's at least significant, right? Like, even if it, I don't know. It's just, that's crazy that, because the astronomy is all about finding your position and on the ground and all that with the stars. Well, that's a field or an aspect of it, but that's like a highly sought after feat, right? Like, that's what makes the globe, right? How come I can use the stars? Stellarium's a globe tool. Okay, if it's a globe tool, how come it's not deriving your distances and elevations correctly with occlusion timings? Unless I, give it the input first to even give you the attempt to do it. So,
can you use your methodology in the Southern Hemisphere?
Ooh, we got a guy doing some Southern Hemi measurements now. Has not been tested yet. We don't have any Southern Hemi lads that have stepped forward yet. There is a call out, though, for anyone who has the ability to record at night. If you can distinguish a peak and you can record stars at night, get a setup and go record and send in the data. We could figure out everything after that. That's all you need to do. We just need your latitude and longitude of where you recorded from and the peak that you were filming. Yeah, we have some potential Southern lads coming through, but just kind of waiting to see what happens.
Do you expect any difference in the southern observations? Like, what could be different about that?
Yeah, I don't know. I don't know if it would be different.
No idea. Yeah.
If you're just going off of Stellarium, then you don't really need a physical observer. In the South, can't you just do it on Stellarium like you're doing this other stuff?
No, it's literally based off of a physical occlusion timing recorded by an observer. The purpose of using Stellarium isn't to circumvent an actual measurement. It's to reference where the star was, because it's the easiest way to get the calculated value using 15 degrees per hour and all that with the true position. It has nothing to do with like, making the observation relevant. That's actually retarded rhetoric.
No, where's the proof of, like, if a Glober did this, we'd want to see video footage, right?
Of the stars being occluded, and then we reference.
Yeah, but where's the timestamp on it? Where's the video of the video of the?
Yeah, there's
Don't
tons of
hear it?
videos of it. Why are
Yeah,
you like you've been a part of this process this whole time now, and you've chosen now to try and argue rhetorically over nothing? That's like the dumbest move ever. I don't approve.
Well, bottom of the barrel right there.
You guys aren't even going to hear people out. You're just going to mute people and insult them. What are you doing?
Yes.
Yeah, when they're talking over somebody that's currently talking.
You
Yeah.
didn't even hear her out. What her even point was.
Her point was, you need to take a measurement? We literally have measurements of it. We're going out and taking measurements. The whole purpose is to go out and take a measurement. The purpose of it isn't to sit here, make a video, clip our answers out of context, and then act like we didn't have any answers. If you think I fuck one give about anything she's asking, I don't. I already answered it, and then she's talking over me in the middle of me answering it. She doesn't care about the answer, bro. Which means I don't care about it.
She asked for.
So yeah, when someone comes in here and they're like, "Hey, I don't know a fucking thing about the process," and they start talking shit, yeah, I'm gonna talk over them. Don't care, and encourage them to not do it again.
That's the thing. It's just faux good faith. Last time we entertained every question that Russell asked, and she clipped everything out of context to make it look like they were saying things they didn't say, and then completely straw man the presentation to make a really shitty hit piece.
You have to give people. You have to be patient and give people a moment to say what they're saying, to clarify so others understand. I know there was a little over talking there. Maybe she was delayed. She did overtalk Alan, so maybe there was a little over talking. But I mean, she was trying to ask about how.
Yeah.
Geo, her question was
Geo, hold on.
specifically, are there
Geo,
videos that have a time?
Whoa.
Geo, I did that last week. The whole week, answered everything she asked to completion. Even when people were interrupting and saying, "Don't answer the question, she's being retarded," etc., answered everything. Made a whole video cutting out our answers and making it seem like we didn't answer them. And then to sit here and be like, "Don't you even?" That's just rhetoric from fucking Ruhef, bro. I don't give a fuck. I don't have to hear that out. If it's not enjoyable for the audience to hear that, that sucks. We're on episode 16 of this. There's people that don't understand a fucking triangle, and they're trying to act like we're lying about it. Like
Every video that's been published has been timestamped as well. Every video that's been published has been timestamped. So, I mean, if the person is really sincerely wanting to have a good faith question or conversation, then how is it that they don't know that every single video from Globers and from Flat Earthers have timestamps on them? That's lame, especially if you're making hit piece videos.
All right, well, that could have been explained, though. Instead of just muting her and moving on, you could have explained that so other people who are listening. It's just
That
getting to the
presenter's
point where
suppression.
yeah, I know. The thing is, it's just getting to the point where you guys mute and shut down everyone who brings up a question. So why even ask for questions? If you don't want
Everyone that brings up a question.
That's not accurate.
For you? The questions
No,
aren't good
no,
enough?
That's Geo. That is not accurate.
Yes, it is accurate. You mute
that's
every
kind of
single person who speaks. Everyone
That's
in
not
here
accurate.
Every single
Everyone
person,
in here has been muted before their points were even completed. Zanuck was muted.
Including
Russell
yourself?
was muted. John was muted. Everyone in here was muted
Bro,
before they even.
what
got to
happened?
ask the
What happened?
question.
What happened when John? What happened when John got to do his thing to completion? He did the exact same thing that he did every single fucking week, bro. Just to track.
You called it, Gio. You even said that he did exactly what Alan said he was going to do. Week after week.
Yeah, but you can talk these things through instead of just muting people. For example, why does it show 219
Yeah.
with the Theodolite? Yeah, why does it show 219 with the Theodolite? So you could address that, for example, instead of just muting them, insulting them, and moving on. It's just not an open discussion. It's not what we generally do here on Earth Awakenings. You guys are running it very differently. Generally, in presentations, people are, when they're presenting, they can kind of choose who's speaking, who isn't, more so than in an open panel. But this is just getting to a point where it's just like a totalitarian situation here. You guys are shutting people down. You're not answering questions. You're not actually going through this for the audience who's listening. You got to keep in mind, most people don't know the answers to all these things. A lot of people haven't heard it before, so they don't know. So if you ask a question that sounds simple, it may sound redundant to you guys, but maybe a lot of other people haven't heard it and they would like to go through it. Otherwise, it just looks like you're muting and shutting every single person who asks a question down. Why even take Q&A if you're going to mute everybody?
John's heard it.
Yeah, John asked a question that has been asked and answered several times. We've done 16 updates. Calder asked a question that was completely unrelated to the topic. Rusted Soul asked a nonsensical question that had nothing to do with the topic, so she could make her hit piece. I don't know why QOP was muted. I don't know why Zanuck was muted, but most of those people were being bad faith.
Sorry. So QOP was muted for asking about refraction between the observer and the object doing the occluding, and that has nothing to do with the occlusion side of it. And I muted him to continue on with the presentation to get through that question because that was part of it, to answer that. So interrupting in the middle of that. And that's something that we've already went over. And the thing with John, right? We talked over it multiple times. We're on week 16 now. He's only showing up to rhetorically do it to, be annoying or whatever. And like, I don't have patience for that. And you're right. I am sorry about that. And I know it's been getting a little totalitarian, as you said. Totally agree. And it's a wear on my patience with dealing with dealing with the same stuff every week, where it's like, do you have an actual question that's meaningful and not trying to obfuscate or just have no physical meaningfulness to it? I mean, we get Zanuck in the conversation. He starts talking about things that aren't even relevant to it. And it's like, it could be this, it could be that. It's like, bro, we have a whole series of videos documenting the occlusions, where it's at. Like, there's no, like, what, like, I don't have time to listen to that. And I know I was being a little short and abrupt with him, and I apologize for that. But in terms of the other people, it's just like rhetorical nonsense, and it's getting frustrating to deal with, man, because I'm trying to genuinely help people do this, present the data, make it digestible. Nobody asks anything. And then the people that do ask stuff are like arguing rhetorically or jumping in head first with no actual understanding of how it works to try and like debunk it right off the rip. And it just gets super frustrating. And I do apologize for that. I know that's not how you typically do things.
Oh, real quick, in Alan's defense, I want to say...
No, not in Alan's defense, Lily. Just...
Authoritarian.
Maybe let Xander talk?
That last girl's asked for timestamps. That was stupid.
Crazy, because there are timestamps on all these videos.
Well, this experiment is about data that relies on time measurement. So I mean, just kind of ridiculous.
Wholly ridiculous. The timing of the occlusion is what we're doing. That's a timestamp.
In the previous person, it seems like every glober doesn't get a refracted mount and can't block the light, right? Taylor's provided that experiment with light and water and a laser with like a knife, and if the mountain was refracted, it wouldn't block the light. So that's the whole point of it. It eliminates the refraction. Am I incorrect there?
No, they know that.
I'm interested in that refraction experiment because the occlusion happens when the light is blocked. So if the light path is refracted and the mountain also appears to be refracted, it doesn't matter. What is mattering is the blocking of the light path. And I'd be interested to see the relationship between Taylor's experiments and the actual observations in terms of what the light path looks like in Taylor's experiment and how it relates to the mountain.
Honestly, as a listener, I would really like some good faith questions, because the stuff with going over with Jesse and John and these guys every week, it is, as just a listener, like, it's rough. And so it would be nice to have someone actually be able to still man the premise and ask a legitimate question that may be in regards to it, that would maybe refute some of this stuff, but that's just not what we're seeing. And so I don't know, I hear your frustrations on it, Gio. I think it's this whole thing.
I think you broke up at the end there. Well, yeah, I mean, people have questions, but I mean, there's a thing about being patient and hearing out people's questions and then clarifying, because some people, maybe it's the first time they've heard it, you know, maybe they don't understand. I mean, the thing Rusted Soul asked, so she was just asking about, are there videos with timestamps? Maybe she hasn't seen them. Maybe she's not aware of them. Maybe she hasn't looked, or whatever it may be. And she was just saying, couldn't it just be done from Stellarium? So there's a whole answer to that. No, it can't be. It's an actual observation from the ground.
I'd like to address both of your points right there, if you don't mind. First off, people who are coming in here new, those are not the people we should be taking into consideration. If people are coming in here new and wondering what the hell's going on, then they need to just get back to this channel where it's all been recorded for this many weeks. And the people who are new to this need to review all other 15 recordings before showing up live Monday night with new questions or what they think are new questions. The responsibility there is on the new user, okay? Not us.
Wow.
Okay. Secondly, Rusted here in this call out about timestamps needs to learn to read the room. Is it that all the other people on her side of the fence, or seemingly on her side of the fence, are also calling out this issue of timestamps? Or is she the only one in the room who's mentioning something as absurd as faked timestamps? When we have people on both sides of the fence who are now participating in taking measurements, getting timings of their own. That is not what is being called into question here, and Rusted needs to read the room and eliminate the irrelevant question because nobody is asking it but her. Are we good, Gio?
I don't think you should be good with that. That was pretty awful, actually. What a horrible take.
How so? How is it horrible? What did I say that was horrible? Lay it on me.
Number one, Gio's got a thing here where we have new people come to show up for events and things like that. And basically what you're saying is that you don't think that somebody who's giving lectures should know how to incorporate new people into the situation. That's just a bunch of
that's exactly what I'm saying. When we're talking about a series of presentations on the same subject, hey, Coco, you spoke, I speak. You speak, I speak. Got it? Shut up and listen to the answer.
No, you don't.
That's how it goes. That's how it goes. Now, the answer to that is,
well,
the answer to that is yes.
Him? I
don't interrupt people.
Yeah, you shouldn't.
I don't interrupt people.
You shouldn't be interrupting you. But yeah, I think it can be a bit more respectful to a woman.
It was addressed
I don't
to
see
me,
it that
and
way
I
at
don't
all.
even get to
When
respond. He addressed me,
Rusty,
and I
you
don't
might
even
get
get
to
to
respond, but no, I was responding to Gio for the points that Gio was making. Okay, I don't care who takes advantage.
You made a
or takes
claim that
exception
I
to what I'm
haven't
saying.
seen the video.
So why are
That's
you interrupting
not
me
true.
again?
Because
I didn't make any
should
such
be able
claim.
to defend myself. You did. You
I
said
didn't
someone
make any
like
such
Rusted,
claim.
who comes in here and hasn't watched the videos and hasn't done their research.
I did
That's
not
what you
say
said.
that.
You used my name, bro.
You
Let's
put
just.
words in my mouth. What I said about you is that you
second,
need to
lads.
learn to
We're getting
read
into
the
a-
room
We
when
got-
you're calling it a
one
challenge.
Yeah, 1 second. We're getting into a full detraction here. This is a full sidebar that we'll come back to after we wrap up here. But Gio, I do want to apologize. You're absolutely right. I do need to show some patience there. And there is nothing wrong with a new question, coming into the conversation or whatever. But I was annoyed at at her for asking the question because, one, it's not a legitimate question. It's a rhetorical device that Ruhif and Jesse came up with to try and make it seem like you don't even need to do a measurement. So it doesn't come from a genuine place. And secondly, I was annoyed because last week when I specifically gave all the attention to answer any question that she had to completion, turned around and made a video cutting out all the answers and acting like I didn't answer it. So that was super annoying and kind of took that out on her a little bit there. But I don't I see what you're saying, right? And I know that's not how you operate things here, and I do apologize for that, but that was my own frustrations, and I will do better in the future. Apologize for that. It's been extremely frustrating.
We love you, Alan. We love you.
No, I hear you, and I know it is challenging in a lot of ways, but it just when there's a whole community, people are all in different places of their journey with this, of what it may be, everything, and then they have questions and inquiries that they want to ask, and yeah, some of them may be remedial or even repeated or whatever it is from other people, but it just seems like like if you're in any way like a presenter or a teacher, there is something that goes with that. Like if anyone is, I'm saying, of being receptive and patient to questions. And of course, there's different questions for different times. And maybe there's a more advanced question time. Maybe there's a more beginner question time in some cases. But I mean, because it's just the last couple of weeks, there's just a lot of like, you know, muting people and not really letting the conversation continue. So I just don't know how in a open community where there's a lot of people that have questions, how, you know, you can actually have an open engagement when people are always just going to be muted because the question is not, or it's either frustrating or it's not something that you want to hear. But I mean, if it's a question, it just seems like it needs to be addressed so that other people can hear it and just get the truth out and the clarity to it, even if it takes 30 seconds or a minute or two or whatever. But it's just when people are muted and it's shut down, and then the other people don't know why they were muted exactly, and then it just ends up being kind of a more closed off thing.
No, I got you. The issue was 100% on my end.
I mean, I want to hear new questions. I just don't want to hear the same 6 questions that we've been answering for 16 weeks. That's my thing, right? And if I can ask your question before you speak, generally, like maybe it's not a good question, but new people hopping in, I think I have a different position. I definitely want to hear new people coming in, what they have to say and what their questions are, to be honest.
Can I ask a couple clarifying questions?
Yep.
So these occlusions are recorded, correct? And they're recorded by both sides. So my understanding is that it has to be recorded in order to be entered. I mean, that's like part of the process, right?
With the timestamp.
Right, with the timestamp. But didn't I hear someone say that the timestamps that are recorded by the observer can actually be verified using the video without having to look at, like, having a starting point? They can go by frames or something like that. So what they actually recorded themselves as the time can be verified as the actual time.
Yeah, I see what you're saying. So if you know the time when you started the video, right, and then like if the video is playing at like, well, you know, 1 frame a second, then the length of the video, whenever it gets occluded, you can add that time to the whatever the current time is when you started the video, and that'll be the time of occlusion, if that's what you mean.
Yeah.
Like if it's
So
not,
basically, we're not talking about we're not recording any trust me bros from either side, right?
Correct.
Everything's verifiable. And so, and then the other thing was, I know I keep hearing about the refraction on the other side of the mountain. I don't get that question. Because if you don't see anything, there's no refraction.
Well, it's the most sensible question on their side because the refraction between the star and the mountain peak is what facilitates the change in occlusion. That's what causes this light source to have to be further below or further behind the Dow when there's a medium added to it. That's why it has to be physically lower, because that physical intersection point changes because of the refraction. So there is a refraction amount. It's just not to the tune that they incorporate.
And I guess my last question is my understanding is the reason we're using occlusions to begin with is because if you strictly want to use a theodolite and you want to incorporate celestial and terrestrial refraction and, you know, calculate your way through it, you can come up with a sphere every single time. This is like, let's put it to the test. Does it really test out that way? Is that, I mean, is that kind of accurate?
Yes, because the mountain provides an angle for there to be a physical intersection between you and the light source. So if you consider the star as like a flashlight, right, that's always in motion, but it's really far away, right? The light that you see from it isn't necessarily going to be the light that's coming from the actual source of it. So you're always going to see this, like, you know, this dot projection, but the actual source of it's always going to be ahead of it.
All right.
So
I
we,
think
so
I
we,
had something else, but I can't remember it.
yeah. What was the last part of your question? Because that was a two-parter. I only got half of it. I thought there was another
I was
aspect
just
to it.
asking about it. You know, you can use the theodolite. I mean, I've heard them say. I
Oh,
think it
right,
was
right, 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 right. The theodolite. That was the other half of it. Right. So if you reference just the optical, looking at it horizontally or whatever, right? Like that's what the optical angle looks like, and they are asserting that that's not an optical angle. They're asserting that that's physical. That it looks that way because it's physically lower than you. And if it's physically lower than you, then that's going to correspond to a different intersection angle between you and the star to get the occlusion.
Thanks.
But you can't derive the elevation or distance using the theodolite optics?
Only by inputting, only by first inputting in the globe parameters to start with. So when I went over earlier at the beginning with this spreadsheet, I think Shane just put a link to what it looks like in the thing. Let me scroll up to avoid lagging out here. See if I can find it. Yeah, that's right here. So when you start out with the elevation and the distance to get the angle, you can turn the angle back into the distance or whatever off of it. But you have to start with it circularly. It can't be done independently.
Yeah,
Yeah.
so that would be a good point to bring up. When these guys go optical, I get you guys are frustrated with it. It makes sense why you would be, since you've been deeply involved in this and going to a lot of different channels and communities and discussing it. So it makes sense, but like that's an important factor. Like if John's theodolite optical can't derive the distance and elevation without these added factors, that would be a good thing to let people know and let them know that that's the case.
Oh,
And that,
Right. Can only
yeah.
be post-dicted with all
Well,
the parameters. Exactly.
well, that was our starting premise, and then he was like, "Hey, let me come in and talk about something that's not that," and then he talked about the thing that it was. So,
Well, yeah, but
it's like that's why it's like the worst, because we literally just did all of that, and we've been doing that, and the only thing that they do is just the same thing, is to just pretend like we didn't.
no, I hear you, but there's that phrase, "The truth doesn't fear investigation." So if people are investigating this method with
That's
things that are not true, then if the truth should be able to shine through and just allow the questions to flow like water, and then refute them, with the truth of whatever the truth is. If there's
that's true, but the truth also gets annoyed as fuck.
If you could train an
I heard.
train an LLM for the basic questions that'll you could divert to. They could do the work.
I might
Yeah,
have
so
missed it, but what was the
Unnecessary.
explanation for using the globe distances? You probably already said.
Oh, for using globe distances. Distances are units of measurement that are derived from the spherical coordinate system of the graticule itself. So like a meter, etc., is 1/10,000,000th of a terrestrial meridian. So that's all it's related to. So when you say like a globe distance, all a distance is just a unit of measurement within the coordinate system, so that it's like internally consistent. So when you take angles to stars to quote unquote, derive a distance to it, if you traverse that distance in units of measurements derived from the coordinate system itself, it's going to be consistent. So there's no issue here with using a unit of measurement that's there's no such thing as a quote unquote globe unit of measurement. All units of measurement are tied to the coordinate system itself, which is the graticule. It's just a ratio of the graticule, which is just a ratio of a circle. So none of that is necessarily globe inherent, right? It's just a distance value. Now, the real thing that would be globular about this whole thing is if the angle to the mountain, right, was physically lower because it actually had drop over distance of that distance that we calculated. That would be super significant. Someone playing RuneScape in the background? I hear some clickety clacks.
Who's clicking super hard? The new people?
On my mic.
Got a quick question about your error bars from last week, Alan. Have you considered actually trying to come up with an error metric, like based on the timing uncertainty or something like that, to see how error varies across your different measurements.
Give me 1 second. Take the time the video started and add the time it got occluded to your time. Anyway, sorry, what was your question? The error bars. You were saying about the error bars. Go ahead.
Yeah, where there's a way you can actually attempt to quantify the error that might be involved in any measurement that you take, because there will be an error, right, based on the ability to time the things. Because what's the duration of each frame of your video?
1 second, and then Stellarium also works on 1 second intervals, and the sky moves at 1 arc what was it, 1 arc minute a second. So the way that it comes out, we just added like a plus or minus 60 for that for elevation, and then a mile for distance, because the elevation differences weren't very much. So like if you add like a large number, it's not gonna, or it's gonna make it indistinguishable for pretty much every measurement. And for distance, like a mile's, pretty significant difference. So you should at least be better than a mile. So when you say like a real discrepancy unit, like I'm not quite sure what you mean, because
So
things are what they
it
are,
seems to me,
and we get snapshots of the information back to us in 1 second intervals. We record at 1 second. So I feel like adding a plus or minus 1 or 2 second interval there is not the worst thing to do.
I guess it's better than nothing, but I'm just thinking that there might be a way that, the same way Dr. Heffron said that Theodolite, their angles, their ability to measure angles as a function of distance, or the ability to measure a height as a function of distance rather than the angle is the problem. Whether there's some metric in this maths that would result in an error that is proportional to the distance or proportional to the angle or something like that. That might give you a good indicator of how precise everything is for different observations. I don't know what it is, but there might be something.
Dazza, do you agree that the numbers when input for Pikes Peak are exclusively flat Earth as an outcome?
No, I don't think so. No.
Why? What part is wrong?
Well, I think the part that is wrong is the way that you work out what the globe model would show, because we know that the full globe model, right, can predict the actual observed angle from both Heffron's place and from the peak. And so to say that the globe model doesn't match is fundamentally wrong.
Well, from the peak, the angle to the star, which is what we're comparing in the method, right, for the globe, would be what at Pikes Peak? Do you know? Do you know the difference in the drop over distance between 50.7 kilometers between flat and globe?
Not off the top of my head, no.
It's like 201 meters, right? So your drop would be 201 meters below, and then from that, you'd want to add how much celestial refraction from the mountain to the star.
Okay, but
well,
yeah. So
if it's wrong, one of those two metrics would have to be wrong, right?
No, I think the whole treatment of refraction is there's something just doesn't feel right. I can't put my finger on it, but there's something that doesn't feel right.
Okay.
Yeah.
Right.
And this is right. It's fair enough to have a gut feel about something not being right. And in particular, and this is why I wanted to discuss Taylor's measurements and try and get a good understanding of what Taylor was trying to illustrate with her thing. Draw some light paths, compare it to the mountain, because the whole what is obstruction or occlusion, and when does it occur, and how does refraction impact the occlusion time?
Well, could we just agree that Pikes Peak then is exclusively flat? Because Rivif made that stance. He was like, "Hey, you got to give that to him to even understand the process, right?" So you do give that one to us to go on to question Taylor about refraction, right? Is that what you're saying?
Well, if everything about your process is correct, then that does align with a flat Earth. But if everything about your process is not correct, then the normal globe predictions stand.
Okay, that's legit and fair. And if you could show us where one of our variant globe procedures is incorrect, I'd greatly appreciate it. Alan's spreadsheet there has 6 or 7 different globe methods precisely calculated. None of them are consistently correct. If you want to recommend a new one, definitely let me know and we'll add it.
Yeah.
Stone, you
So I
hot
think the
mic
big
again?
challenge. Yeah. So the
Oh,
big challenge
shit,
on the
man.
globe
Thanks.
side there is
KO.
to work out what the to come up with a model of predicting the occlusion time that includes terrestrial and celestial refraction.
Well, so
Which have,
we don't agree with terrestrial refraction, but being the good guys that we are, we allow you to argue at every example anyway. And the spreadsheet actually includes terrestrial refraction, which is ratioed at 7/6R, including the radius of Earth, down to the kilometer at 2.4 arc seconds per kilometer. That's what Riff likes to add in. So all of the measurements and calculations do have like a switch for accommodating terrestrial refraction at that rate at the press of a button. And even when allotted that consistent terrestrial refraction, none of the globe measurements actually outdo the flat.
so we know that the refraction exists, right?
Yeah, it's on the data sheet.
Yeah.
You can see.
Yeah, because the height of the angle to the mountain changes over time.
Right.
That's probably some error we could include.
Sorry, quick question for you. So when the globularists want to derive the elevation to the mountain, they insist on using the true elevation to the mountain. They don't use the elevation plus or minus 50 meters or whatever would be extended by the refraction amount. They use the actual one. So like when we're doing true to true, I feel like it's because this is an occlusion process, it is necessary to use the actual timing thing, or I'm sorry, the actual raw angle. But even accounting for refraction, like Shane said, I have all the angles derived there. None of them give the correct distance unless you do it circularly, which tells us nothing unique about anything.
But wouldn't it be fair to say that if you sent a surveyor out there and he was to measure up the scene, measure the distance along the ground, measure the angle of elevation to the mountain, that there would be a consistent view that would match the observed angles and the geometry of the situation?
Yeah, if you can agree that has nothing to do with the celestial theodolite, the method, the testing, or the prediction, then yeah, I agree with what you said.
We don't dispute any of that. Like in fact, when Mike got the modern theodolite or whatever and did the measurement, it gave the angle that corresponded to what the globe would predict as a physical drop over distance, and that is the significant part here, the physical drop over distance.
Yeah, and I think I know. You probably know the reason why I'm using a term that I use in software engineering. That this smells to me. That it doesn't smell right. It's because I know that the measured geometry of the scene is in alignment with the spherical Earth. But your method. Sorry, I cut you off there.
Is it me? No. But that's the best global defense I've heard so far. Is it doesn't smell right. I dig that. Continue.
Yeah. And it's messy, right? And so initially, in the first few weeks of this, there was all of this other stuff going on, and the spreadsheet was impossible to follow. The process seemed very convoluted, which gave the whole thing a whiff of insincerity or incorrectness, and that I don't think you've successfully eliminated that yet. There's still something that's not right, but it's just difficult to explain it.
Well, in the effort of trying to simplify things, what we have now is the most super duper complicated spreadsheet that is trying to accommodate every so far objection, because you understand from your perspective, as you just said, it doesn't smell right. So what we've been getting every step of the way is, well, it's not that globe is wrong, it's that we didn't do the math right. So really, it's your guys' fault that we have 7 different methods to calculate the globe. No one disagrees on the flat Earth prediction. We're the same and consistent every time. The only time what we run into is that each different example has a different reason why the previous predictive method for globe drop and refraction didn't yield the correct result. So Rubif and Jesse and other people will just ad hoc their own explanation with their own difference. And now we got a different calculation for this position. So we've incorporated all of those different methods, and we're trying to look for a consistent globe method across the board for all observations that would work. And there definitely isn't one. The reason that it's so complicated now is because none of the globers will ever say, actually, you're right. That's not for the globe. All you guys ever say is you didn't do the globe right. And that's how we're trying to super accommodate every objection that way.
Shane, I
Yeah,
just
I guess
smelled
that-
what you said, Shane, and it smelled ridiculous.
And what you said something there that triggered a thought too, that the whole when does this stop working scenario, and we've had the conversation before about if the distance is too short or the angle's too steep, there's no differentiation between this and the globe. And then if we go the other way, where the angles are too far or the angles are even negative potentially, then you get in more dodgy territory. So there's this little sweet spot where this appears to line up, but we know that you cannot differentiate on the other side, and in some cases, the feeling is that it won't be close to the globe in any way, shape, or form.
Man, I wish you'd look into some of the data yourself instead of getting a secondhand from Rufus and Jesse, because you actually see the opposite is true. Like, so not only is it not that, but the conditions with which the results become indistinct actually arise because there's a certain ratio of distance and elevation that when you apply the geometric earth drop and the refractive celestial refraction, and they actually cancel each other out. And so what you arrive at is a globe Earth prediction much closer to the flat Earth prediction. And those are the examples that muddy the water, that we rule indistinct, that I think is what you're talking about. So it's not that only the ones that are fitting this ratio satisfy the observation. It's that every other observation does, except the ones that fall in this ratio, where the geometric Earth drop equals the refraction correction, so that the flat Earth and globe Earth predictions are much closer together and thus indistinguishable.
Yeah, it's been delivered to you rhetorically in the opposite, because the globe exists as the specific ratio measurement, not the other way around. You should be able to go anywhere and measure an angle that corresponds to what the globe predicts for the occlusion, not the physical angle of the mountain peak, as if there's no drop over distance between you and the mountain, because that would just imply that the Earth's flat is flat. I'll be right back. I gotta get some water.
So my quick question earlier was simply about the observation that you made in your laboratory experiment. If you have one point where you're looking at the light bending through the prism or glass or whatever you're using, where we all will agree will bend probably twice as it enters and as it exits the glass medium into the air. If you're using that to justify and provide a foundation for your conclusions about, yes, I still see the light no matter where this mountain is or obstruction is, you're forgetting the point that in the reality of the situation, everything beyond the mountaintop light is being refracted. So what I would suggest is that you'd have another point of refraction farther out, maybe toward the target.
I was trying to point that out too. What you would do is set up like 2 fish tanks if you're gonna
Let me
put
finish
like.
real quick.
I know I never got to finish. I initially said this, but okay.
Yeah, so we have a second point of refraction, the same kind of glass, because now we're only doing. By the way, the differential form of refraction is constantly changing angle, so it's gonna be a lot more. Well, it depends on what the angle change is, but I think you're just trying to make the point where this is what we're seeing in this foundation we're basing our whole logic on. If you had one other point that changes the angle, and then you did this experiment, then you would have a realistic view of your test and the foundation for your logic, which you didn't do. You only had one point. So yes, when you do the one point, it doesn't change, and it wouldn't expect to change. But if you have two of them, it would. The star is under a different refractive value, total aggregate refractive net change of angle of the lights traversing relative to level than the first portion, which hits the first glass obstruction that causes the first refraction.
And
Hopefully
and
that
to
makes
be
sense.
and also like so the globe model has like a vacuum of space after the atmosphere, right? So there's the atmosphere that they're not basically accounting for being causing refraction, and then they just got a vacuum, so then you're kind of good. But in the flat Earth model, at least people theorize that there's not just the atmosphere in between the mountain and the star, but there's also possibly a firmament, magnetic field causes people not to be able to leave, and possibly a superfluid that the stars are contained in. So there's definitely refraction we're not accounting for.
We'll back out for 1 second. We don't account for any refraction happening in space because we think in a vacuum there wouldn't be, but we are accounting for the refraction along the atmosphere before it hits into space, and that is significant. In other words, that's why we see the sun slow down as it sets. That's why we see the sun in a position with our testing that says it's about a half a degree off as it sets, whereas things that are 3, 4, 5, 10, 15, 20 miles away are fractions of a degree loomed, or even when there's extreme refraction, it's loomed less, but we're still talking about fractions of a degree, 0.02 degrees or something over, 7, 8, 10 miles, 20 miles, fractions of a degree.
So
That should
Xanax.
be a clue.
So Xanax, for this Pikes Peak observation over here, do you agree that it aligns closely with flat Earth, given all the parameters that Ruhif agreed to and Daza agreed to earlier, or did you want to take a look at it?
Well, I'm going to take a look at it because it is, and as was mentioned earlier, you're talking about something that's over a very short distance, and
Well, 50.7
testing
kilometers.
27 miles.
Yeah, it's enough to
Looking at
tell
it
it.
from here to Catalina. You can do
Yeah.
tests with
Well,
you can test from Santa Monica to Catalina and see these same types of same kind of occlusions. It's not quite. It can be almost due west as well, in some cases. Do the sun, for example. Do whatever you want. You'll see that there isn't a lot of refraction over that period of time compared to the drop. We're seeing 500, 600 feet of
yeah, about 2 arc
drop. So that's
minutes.
why I want to look at the angles.
Over
I want to look
over.
at the angles. Actually, sorry, it's less than that because you're talking about a total height of. I was doing the metric. The metric is like just less than a mile, like probably 0.8 of a mile. There is 1,470 feet or something.
Well, we're looking
meters,
at
rather.
50.7
So,
kilometers. It's like
yeah,
201 meters difference between the two.
0.8 miles over and 27 miles. So we got a 0.8 mile height of this mountain, whatever way you look at it, either looking up to it or looking down from it. Doesn't really matter. That the trigonometry inverse tangent still works. We take 0.8 miles, divide that by 27 miles. We get the same number as 1,400 meters divided by 47,000 meters. There's no difference. And I want to know from your calculations, with expected Earth curve, where that peak would be and if it's the same, then there'd be the amount in our world, so to speak. There would be the amount that made it loom up would be equal to that equality.
Right. So stay with me here on this one, right? We already did all this. So we accommodated over that 50.7 kilometers, 201 meters of geometric Earth drop, which is the difference between flat and Earth, a flat and sphere over that distance. And then we got a geometrically predicted angle, which is different from our flat Earth angle of 231, right? Geometrically, it'd be at 2 degrees, 4 arc minutes. That's just globe drop 201 meters below. It's nowhere near that. The actual occlusion time that we're shooting for is 232 as recorded by Stellarium there. So then we add in celestial refraction with 2,000 meters above sea level with the pressure to get back to our 219 prediction. And that also includes giving you terrestrial refraction at your 7/6R at 2.4 arc seconds per kilometer ratio down that way. So that's your geometrically dropped celestial and terrestrial refracted angle. Couldn't ask for anything else. Still way wrong. Still isn't close to the 233.
Interested to see I'll have to go through the calculations. I've already gone through some preliminary calculations, and it's close. It's not that far off, but it is. If it isn't that far off, can refraction make up for it? Certainly. We've seen a half a degree of refraction under certain conditions. I wouldn't expect to see that in Colorado, looking at Pikes Peak from some position, and also the distance to it is, that's going to be another variable that you gotta, come to terms with, or at least give you range of acceptance.
So the point is, sorry, dude.
No, it's okay.
The point is to make refraction a prediction and not a postdiction. So you ask, is there an amount of refraction that can fix it? Certainly and always, dude. That's what you guys have been showing us over and over and over again. There's always an amount of refraction we can apply after the fact with the known parameters to bring it back into perspective. The point of this is to make it a prediction. And when we have to restrict you to the known predictive formulas for terrestrial with any coefficient and celestial with the known pressure, it fails every time. And that's what's interesting.
It doesn't fail every time. That's kind of a grandiose claim.
Well, every one of these 43 measurements that favors flat Earth more than globe, it seems to fail.
Oh, and your test. Yeah, I'm just wondering if you got the corrected. I'll go through some of the numbers and see what you guys are like. Because if you look at the.
Can you guys let me know when I can ask a question?
Yeah, if you go into like Earth Curve Calculator, it doesn't really answer the exact questions we're asking here. We have to kind of extrapolate from the more technical output, the advanced output, and you still get things like the tilt and how much of the horizon is between this distance and the horizon is being obscured and that kind of thing. That's not what we're looking for. We're looking for the angle tilt down, which I think is half a degree from looking level down to an observer at that point 27 miles away. If you're top of Pikes Peak, and you're looking down to the observer, it'd be about 0.43 degrees, which is similar to the number you guys had with 1.343 degrees, but I don't know, it's not the same. It's only 0.42 degrees. So I wonder if we run the calculations for a flat Earth, whether that tilt angle will change. And I want to go through a bunch of these numbers that aren't, like I said, not what we're looking for, but we can extrapolate and figure out what what equates to what.
Well, that's
Dude, I'm excited, Zanuck, for you to go into the data. Like, I hope you come back next week, like, looking at the data and
I hope he
having-
doesn't just watch Ruhif's
having your
video.
opinion on it.
But just so you know, Ruhif agrees with that 219. That's actually the Ruhif prediction. It says theta r is supposed to be refracted. It's actually theta Ruhif. That's Ruhif's final stamped approved angle, which I'm sure Jesse agrees with. The only way that they try to object to this is to change the method entirely, invoke other angles that weren't observed. Because the only thing that we're using in any of this is the known elevation, the height above sea level, and the time of the occlusion. And from the time we get an angle, and from that angle we determine flat or globe. We're seeing, is the surface of Earth curving the necessary amount for that to be the actual angle from the true obstruction on a mountain of that height? And that's what we're finding over and over again is not. So only by changing the observation point comparison do they even have an argument, which is what they just keep repeating over and over again. Hopefully you have an objective answer, Zanuck. I'd be happy to hear it.
Well, I'd be surprised if those two numbers are globe Earth versus round Earth. There's going to be a difference. If you're measuring round Earth values for the position of the object in your field of view based on the height of the mountain and the distance to the observer, I would be very surprised. I think there might be. You guys are not that you're looking to see. I got them, and we're going to keep on. It's exactly what we wanted to see. We see this answer. It matches the globe, so let's go with it. It's possible that you've found that, and the reasons, of course, we would say. Roof already made that point that there's a refractive value that equals that difference, because we're not talking about a huge difference, but it's I just equate it to the whole things we see over in Los Angeles when looking at Catalina. I mean, those are mountains that are about that high, and the distance is the same. So those are kind of the same angles, but yet we see so much of the harbor hidden, and even with extreme refraction, we never see it loomed up. We can never see the harbor in any day, and that's along the water. So it makes me think that why are these numbers you're seeing, which are more likely to never be the same, why are they the same? So I'm actually not conceding, but I'm interested because that doesn't make a lot of sense to me, especially in Colorado, high altitude, looking up. All these things reduce refraction significantly.
Yeah, well, take a look at the data, see if we're representing refraction in any incorrect way, and definitely let me know. We'll accommodate that. We'll
Yeah, Shane.
Yep. I'm excited for you to get into it, and I think Word Salad had a question as well.
Yeah. So, are you using straight lines to the mountain and star because it's a shorter distance? Like, because we do understand that we don't see imperfectly straight lines.
What?
Like, there's straight lines drawn. Is that just to represent angles, or because
that's
there's someone
to
in the
represent angles when things are not visible anymore, and true, like with using the geometric relationship with the baseline and the relative elevation of the peak. So like the hypotenuse part, that straight line going to complete that triangle is just the line drawn from when it's just a tangent from when the star isn't visible anymore. Like, yeah, we see in curves and all that, but like the triangle there doesn't represent a visible object.
Were you talking about a specific diagram?
All of them.
Just generally, because like a Glober was like in the chat, he was like, "Oh well, when I draw straight lines to Polaris, it would never drop below the horizon," and all the nonsense. But yeah, I was just clearing that up. Thank you.
Cool.
Nice. Any other questions? See, everyone's unmuted. That's
I got
good.
one more, if you can stand it.
Absolutely.
So I'm sitting here listening to the not the last guy, word salad, but the two before, Dane and Vanek. Anyways, my question is this: I know on the or on the flat Earth prediction, we're just doing a plain, uh, just a planar trig calculation, as though it's a plane, and what's the mountain peak's elevation above whatever elevation the observer's at. Correct? We're not adding refraction or any
Yeah, we're going.
celestial.
Yeah, we're going raw for raw because occlusion, physical process.
So when they see, now that's the part I don't get. I understand refraction. There is refraction. Refraction's real. It can affect where you see something at. As opposed to where it really is. But when they're adding in all this refraction so that they can bring their mountain peak back up, are they actually is anybody actually saying a refracted image can block the star? I mean, isn't that what they have to be saying? That if you let us refract it back
I mean,
up,
they're certainly implying it, right? Because the actual geometric angle is 217, and they're concerned with where the star visibly was when it got occluded. So they're trying to be like, well, it says it occluded at 218 because that's the relative optical angle to the mountain peak, and the star's refracted position was 218 at the time of occlusion, so therefore globe. And they're very satisfied with that because their interpretation of that is that was the physical intersection point of the star to peak. But then when we go to stellarium to look at the physical intersection point to star to peak, well, we find that the star just intersected the peak at its true elevation, and not the elevation that is predicted by the globe, which is the elevation minus the physical drop over distance. So they have like an unsubstantiated angle there, and they're like, oh, what do we do with that?
all right. Well, I mean, I know that when I look, there's a lot of globe predictions there to choose from. And I don't even
Oh,
really look at them because I don't understand each one and why
yeah.
got 7 different ones. And
I'll run through them all real quick if you want. Because what I'm going to do for this obviously is give extended notes for everything so someone could just scroll through and for prediction. If you're doing a physical process, all you need is this section right here, flatter, this blue tab, and this one for raw globe. All you need is these.
Nobody can hear you.
Testing 1, 2. Like
Super robot, yeah. As soon as you started streaming, probably, and I can't see your stream.
now can you hear me?
Not good.
I'd give it a shot. I think you're all right.
Never
Never mind. Never mind. It's terrible. No, don't do it. Abort.
I was with you, Shane. I thought he said something that it was pretty clear. I thought, well, you're good now.
Yep. Yeah. That one syllable word sounded terrific. Let's give it a shot. Spin the wheel.
I can see there's an orange bar. It's definitely not going to work.
Sounds great now, though. Probably.
Oh, awesome. It turned into a green bar. So I guess. Anyway, okay. So everything you need is in the blue and orange columns here. So this will give you raw geometric globe, and this will give you raw flat Earth. Now the angles under it, denoted by epsilon globe, is the celestial refracted position. And then this green tab here is a refraction analysis tab. So all this is just related to refraction positions and stuff like that. So you're not going to get any distances or anything out of that unless you want how much lift there was. You can calculate the lift out of the green tab here. This tab here calculates our drop over distance and subtracts it or converts it to an angle, subtracts it from the flat Earth prediction, giving the raw globe. So giving the 216 or 217, and then we give terrestrial refraction back here to give them the 218/219, depending on the temperature or whatever. for that angle to derive distances and alleys from. And then we have spherical trig down here, where we have a line of sight, which is I think a chord, and then we have some spherical trig here. One of these starts off with the the gamma angle, so the angle between the radius and the observer and the peak, and then you can do cosines and sines off of that or whatever to get the what is it, a great circle and the other one's an arc, a great arc, and I forget the other one, but anyway, spherical trig functions are down here. And then using raw value, this is with the refracted values, this one's with the raw values, just to see what the differences are when you input the trig, the spherical trig there. And then we have gamma globe. What was gamma globe? Or no, that was mu globe gamma. This was raw globe with spherical trig as well, just different types. So there's different equations that were.
And again, this is your fault, Globers, for always coming up with a different method for it never being wrong. Okay, this is your fault.
I think this one is dead on or whatever. This one was like the baseline to make sure the other ones were calculating correctly. So this is just the benchmark to make sure that those were right. And then down here we have circularity checks for different derivations that we've went over, where we can adjust the parameters to see if we adjust the input parameters to see if the output parameter changes as well, to see if it's circular. And then over to the right, we have a summary tab. So this gives the differences for flat globe, refracted globe, and celestial refracted globe and terrestrial refracted globe. Celestial refraction stats output over here, and then drop over distance, that kind of stuff down here. Hopefully that helps.
Yeah, it helps. I appreciate you taking the time.
Dude, who knew there were so many comparatively equal methods for calculating Earth curve that are always wrong? Who knew, dude? I guess, like, I know I learned that, you can do it 7 different ways. It always comes up with the same.
The spherical one's pretty close, but in most instances, but the input is the output kind of thing. So, but that one gives the most closenesses.
I have a question, if I may.
You may.
Oh, thank you. Are you aware that if Earth is a globe and if astronomic and terrestrial refraction is true, then the angles that Heffron's method give are exactly what would be expected on a globe?
No, because what we're looking at right here, right? The globe has this amount of celestial refraction. So like for Pikes Peak, for example, they predict 12, or I had 14 here, I had the wrong number. But anyway, this is supposed to be a little 12-y here. So anyway, when you tell a stellarium that you're over here and they say, hey, your star is over here, but it's being lifted up by this much and it makes it 217 relative to this peak down here, you're like, okay, cool. But the occlusion didn't actually happen until the star was at 232 relative to the peak and not relative to the observer. So the star can't be 12 arc minutes below this peak, but also get occluded when it intersects the peak at when it's within 2 arc minutes of the peak. So the hypothesis of what you just put forward, it doesn't give an agreement with what the globe predicts. So when you just look at the optics, like, sure, yeah, it would look like that. But when you look at the cause of the occlusion, what actually caused it, this intersection here, this angle corresponds to there being no deviation relative to the observer. Whereas if there was, this angle would be smaller and it would have been occluded at a 2 arc minute difference here with respect to the 219 instead of being at 230.
Well, I can prove my claim. Would you, not necessarily today because you probably don't have time, but would you be up for going over my reasoning sometime to the point where at least you could strawman or steelman my argument, even if you didn't agree with it? Because if my claim is true, that's kind of a big deal. If the globe actually predicts all these angles that Heffron got, and that I got, and that you got, and Goose got, then that's kind of important to know if the globe does predict those, right?
Absolutely. we will go over those next week then. Are you available next Monday at 8?
Is that probably 5 my time? Let me
Fantastic.
Just make a
let me
date with
check.
Jesse.
I'm a working man, you know. So
Yeah,
I
if our
might
schedules happen to intersect on Monday,
I'm
time
okay,
will be made available for you, of course. But yeah, we are going to wrap up
thank
here.
I only have one customer scheduled. That's the 25th, right? Yeah. So
But
Where are you gonna take him?
there's a reasonable chance that I can be there, and I will try.
Awesome.
But Jesse, you two agree that 231 is closer to 232 than 217 for Pikes Peak, right? I'm just making sure. I'm trying to run the gauntlet, make sure we get the basics across.
I was late for the show today because I got home from work late, so I don't know what the context is to that question.
I just asked you the basic observation of Pikes Peak 16 weeks into the extravaganza where you've modeled it completely. You didn't recognize the. I'm sorry. Do you agree? do you agree for Pikes Peak that 231 is closer to 232 than 217 is closer to 232? You agree that 231 is closer to 232 than 217, right? Or 219?
Oh, just as numbers?
Just
Wait,
like as
wait,
numbers, because that would
as
be
numbers.
the Heffron method that we're comparing, which is angle to the star from the mountain. That's the Heffron method. You agree that
Yeah.
in that case, Pikes Peak. Okay, all right, cool. That's it.
And Rosa is even closer. Rosa's like almost spot dead on. But do you agree that the Blinn Mountain, as seen from Edith's Hook, is closer to globe than to flat?
No, it's indistinguishable.
Why?
Yeah,
Why is
and it depends on which one, because there was elevation adjustments that were made, which like I said, like I don't dispute the way that you measured it out with your monitor and all that and did all that, but like, dude, that's not like we're using actual distinguishable peaks for it, not the lowest possible thing to try and make it indistinguishable. So like only when you do the selective adjustments to them do they become indistinguishable. If you like rounded it off and used the peak as a whole or something, it would just be uniformly indistinguishable. But what's really interesting though about your prediction is that in both cases you're off by the amount in terms of deriving the elevation back. You're off by the exact amount that you predict as drop over distance. So in other words, when we look at this occlusion over here and the angle difference between 231 and 217 there, like what happened was you were off by the physical amount that you would predict should be lowered by. So so the drop over distance between you and that object doesn't exist at all.
So I'm confused about this claim of indistinguishable because the distance was over 25 miles. The difference between flat and globe is like 131 meters. How is that
Let's pull it.
indistinguishable?
Ooh, well, let's pull it up. Let's see what happened there. Let's see here. Got North Peak. Change this to graphs. Pikes Peak. Or no, wait, what are we doing? We're doing
Blinn.
Blinn. Which one are we doing? Are we doing Edis or old?
Yeah, Edith's Hook to Blinn. Yeah.
Edith's. Okay, so I got 3 cap for that one. I got oh, what did I do wrong?
You got to be smarter than the button.
I know. Second.
Yo, Jesse, how do you feel arguing with flat earthers about the stars proving the flat earth?
Let's not derail if we can avoid that.
It's so weird. I got it on the bigger one. I was trying to get it on the smaller one, but I'm having some technical difficulties there. So for this one,
I think I found mine.
yeah. So for this one, real quick, the elevation came out to be. So we derived an elevation of 457. You derived an elevation of 554. So with the 60 meter elevation difference, we're with it. You're not 60 meters better than us, right? And then and then that puts you within 60 meters of the elevation. You're actually off a little bit there, but it puts you, within range there. So we're all within the tolerance there. And even if you don't agree to it, like that's fine. But that's the metric that I set for indistinguishability, because we got, basically the same there. And then for distances, we got 56,000 meters. You got 51,000. The actual distance was 49.
And it just to be clear, that's one of the instances where the elevation and the distance ratio matches, where the geometric Earth drop would drop off and exactly inverse the celestial refraction. So for this particular example, I got 22 arc minutes, 4 arc seconds for Earth curve drop, and 25 arc minutes, 7 arc seconds for vegetable refraction, which only gives a difference of 3 arc minutes flat from globe for using the proper Heffron method. That's what we were talking about with indistinguishability, and when picking examples that the ratio of elevation and distance match thusly.
So you're saying,
real quick,
Oh, go ahead.
sorry, if you look real quick here too, and this is an extremely important factor in regards to globularity, because it explains why these occlusion angles always are up here, and they don't line up down here, is because this drop over distance here, predicted amount is 131, and then you guys ended up being off by 131 based off of the the raw geometric globe for Blend Mountain there. So you're always off by that amount because it doesn't physically exist to the peak, and it comes up exactly because it was derived to create the angle in the first place based off of that distance. So it's like it's circular in that regard, but it's circular because it never ends up being manifested, and you can never be better than that angle because you started with it being with that as the subtracted baseline to make it look like, to use the optical angle of 217 rather than 231. So it's like, even though in the instance where it appears like you have a closer elevation or a closer distance, you're actually still off by what was actually predicted as the drop over distance for the physical elevation.
You be fussing at me. So don't you be fussing at
Oh,
me.
Ken, you're hot, Mikey.
I know you
He's
are.
playing with
I
his
want
dogs.
He found his lighter though.
Found his lighter. He's playing with his dog. Sorry about that.
Well, so the 3 cap was 3 arc minutes below the globe geometric prediction, right?
Let's see here. Geometric globe was 41 arc minutes. Target occluded at 38.
So I'm looking at my spreadsheet, which is different than yours. It says that 3 cap was 3 arc minutes below the globe expected and 14 arc minutes below the flat Earth expected or predicted, both geometric. So
Yes.
So I fail to see why that would be considered indistinguishable when it is 25 miles. It's farther than some of Heffron's closest ones. And
No, because sorry, go ahead.
The difference between flat and globe is 131 meters, and mine was drastically closer to the globe. In fact, on the wrong side of globe of flat.
Well, see, you wouldn't be off by 131, right? You would be closer to the actual amount, right? By that amount, you wouldn't be off by it for that, number one. And then
What do you mean I'm off by 131?
The subtracted amount to create your angle in the first place is your drop over distance. And when we derive the distance based off of the occlusion, based off of your physical intersection angle, off of your raw globe there, you end up being off by that same amount because this star here got occluded at someone's hot micing, got occluded at 231 or 233, not 217, not 217.
So the angle returned by Stellarium set to ATM off at peak would be 35 meters below the geometric globe prediction. So I'm not sure why you're saying I was off by 131.
Well, what you're talking about, Jesse, is that you're doing the subtracting the actual geometric earth drop from your prescribed height. So when you start, when we get to get your angle prediction, you're doing the arctan of your already previously dropped earth drop, 507, 511 over the distance 40,900, and that's how you're getting the angle. And then when you're saying, oh, I want to measure it, you're going to add that amount back in so that you drop your refracted earth curve angle back to what it was before to do the measurement. It's the same thing that Ruhif did, except you removed the first step to confuse everyone. Was there any other questions? What do you guys think?
I'm just asking why he keeps saying I'm 131 meters off. Off from what? The geometric globe prediction?
Off from the actual physical elevation of the mountain. But you're not but the reason that you're off by that amount is because it's the amount that it didn't get occluded by.
That doesn't make sense. I mean, the geometric globe angle.
It's very precarious. I know.
Is Jesse hanging on to one observation and ignoring all the others? Is it?
Well, he did agree all the others matched flat before we got here.
Hold on. Hold on. In particular, in this instance, he's not doing that. We're discussing the drop over distance because in this it equally applies to all observations. So in talking about it in this one, we're talking about all of them.
Thank you. Got a
But-
little confused.
But so what he's doing is dropping the height to get his arctan rise over run. He's taking a smaller rise than we are, and then to get that's what you get for your predictive angle. And then when we want to measure distance with it, he goes, "Oh no, you're not doing it right. You got to add in that 131 that we just subtracted back to get our differing angle, so that we can take proper measurements," which is circular.
I'm trying to talk just about vertical distances and angles here, because that's simpler. That's where we're started. Do we agree that on a globe the predicted geometric angle would be the arctangent of the rise minus the globe drop divided by the run?
No, I don't agree. I don't like that. I like doing arctan rise over run minus a subtracted separately calculated geometric earth drop to start. That's the actual method, but you can do it your way because they arrive at the same amount, don't they?
So we do agree that that is correct.
No. I specifically disagreed that your method was not correct, but that it also produced the same results.
Oh, it's incorrect, but it produces the same results. So,
yep.
Okay, so we all agree that angle, we know what that angle should be. We know what angle this altitude angle was on 3 cap at the time of declusion, right? And that angle difference was about 3 arc minutes, right?
I got 14 arc minutes. What are you talking about?
Yeah, mine is different too. For using the Heffron method for the 38 comparison, I got globe at 47 arc minutes and flat Earth at 54 arc minutes, but whatever.
Wait. Were you talking about the sorry, I thought you were talking about the refraction amount. My bad.
No, the difference between the unrefracted stellarium at peak angle for 3 cap and the predicted geometric elevation angle on a globe, which we don't agree on the formula for, but we agree that our formulas come out the same.
Yeah, what difference did you get?
I got like 3 point something arc minutes.
Oh, the difference in true pause from
Yes, geometric globe predicted
from mountain. Yeah, geometric mountain. Yeah.
Yeah, and then the altitude angle from stellarium on the peak, atmosphere off.
Yep, 3.
Okay, so what is the tangent of 3 arc minutes times of however many meters, 40,902 meters?
Arc tangent, right?
1 second.
Where are the values again?
40,920 meters, and was it the arctan of 3?
The tangent of 3.
Tangent, sorry, yeah, tangent.
What are we?
35.
What are we doing?
Calculating calculating the difference there in the occlusion peak timings.
Excellent. That's what I got. So that's if my measured angle from the altitude angle of stellarium at the peak with atmosphere off had been perfectly equal to the predicted angle, the geometric predicted angle for the globe, then this number would have been 0. But the actual difference was about 3 arc minutes, which was about 35 meters, right? So I was off by 35 meters, right?
Yes. In every case. This applies to Pikes Peak, it applies to Cheyenne Mountain, every single case.
Well, not the 35 meters. The 35
Well,
meters.
the meter amount changes to whatever the drop over distance amount is.
Right, but your spreadsheet shows that my 3 cap or whichever it was 121 meters off, right?
Let's see, for that one, shouldn't have been. It should have been whatever the drop over distance was. Drop over distance 131. You were off by 131.
Right, but we just calculated that I was actually off from the globe prediction by 35 meters, right? Or 36? Which is...
So the way that we derive the elevation for the mountain is the distance times the raw geometric globe angle.
Yeah.
And that gives whatever it would have to, because it's based off of the drop over distance there. So your occlusion elevation derives are always off, right? You wouldn't be off by that because the actual angle of intersection would be the same. The difference that you're deriving isn't relevant to the deriving the elevation.
Oh, maybe I misunderstood. So you're not saying that I was off by 131 meters from the globe prediction. I was off from the flat Earth prediction by 131 meters or whatever.
Well, using the Heffron method, right? The thing that we're trying to refute and talk about.
Right. You're off by to the true elevation of the peak. You are off by what you predicted that it should exactly be on by. Yes. In every scenario.
Okay, so as long as we agree that I was within about 36 meters of the globe prediction, then we're good to go. Okay.
All right.
Thank you.
Good time. Made a lot of progress tonight. Danik, we expect notes for next week.
Dude, not bad. Honestly, thank you guys. And again, I apologize for being a dick. I know my patience have been getting thin. I've been trying to do these every week and be professional, and it's just been getting a little frustrating. So I do apologize for that. Next week, we'll come back with a reset, start fresh, get off on the right foot. Gio, thank you as always for being a gracious host. And thank you for calling out my behavior. It was like, not everyone does that. And I was being a bit over authoritative in regards to how I was trying to present the data. So thank you for bringing me back down to reality, bro.
Oh, yeah, sure thing, bro. Yeah, thanks. I appreciate. I just kind of popped on my mic real quick and just kind of said that. But yeah, man, no, I appreciate you being receptive to my kind of thoughts on that and a little bit of feedback. And yeah, there's probably just a happy medium ground somewhere between that of just when people are asking questions. And yeah, because I mean there are some that may be using tactics or maybe trying to derail things. So it's a fine line as always, but At the same time, a lot of people are coming from different places, you know, in their journey and in their process of all this. So, but yeah, I appreciate that.
Yeah, there.
Absolutely.
It's weird that there are specific people trying to specifically derail it. That's like our main contention, I think, which is weird why that would be in the first place. If it's no big deal and so easily debunked, whatever.
All G. All right, lads, we will see you next Monday for update number 17.